Hi everybody, you're going to hear another introduction very soon. But before we begin, um, this is, by the way, after me solving the entire test and going over every single problem. So this video will probably be super long. And you see how much work I did? That's a lot of work. Yeah, this video is super long. So this is the 2013 ACS National Exam of, multiple choice. And I go over every single problem. Now, I might make some mistakes, obviously, and some things might seem unclear. So if you have a question, leave it in the comments. And if you have a question about anything, leave it in the comments. If you have a concern about something I did wrong, leave it in the comments. Just let me know, and I can get it fixed maybe by telling everyone in the description. Now, note that some of my explanations are not sufficient. Some of these assume that you know the topic by heart. So if you don't know the topic by heart, you're in a bit of trouble here. But I suggest that if you don't know the topic by heart, I suggest you kind of build your knowledge and go study the fundamentals before taking this, because this test is very brutal. It will test you on everything, and there will be new concepts that you might see here, and your goal is to learn. So if you don't know something and you find a new formula or a new concept, write it down, because chances are you'll see it again in a future exam. And this is national, which means it's super hard. And, that's why it's the national level. So a big tip of advice I have for you is not to watch this entire video unless you want to. It's just to go over the problems that you need help on. So you would ideally go over the test first. So do test first, and then you would go into this video and check out the problems you got wrong and see how I did them. Now, for some problems, like I'm going to tell you to guess using some smart tricks. In other cases, which is a majority of them, I know how to solve them. So I hopefully will be able to help you solve them. So, that's all I wanted to say. I hope you have fun. Enjoy the video. Hello viewers, in this video we are going to be going over the 2013 national exam from the ACS. So it's 2013, it's the national exam, and it's part one of the 2013 exam. So if you're interested, check out the link that I will provide in the YouTube description. But other than that, let's begin reviewing this test. So at the front of the packet, we have some constants, some symbols, and some equations. So all of these will probably be really helpful in solving these questions, but most importantly, this periodic table will be the most useful in my opinion. So without further ado, let's get started. So let me switch over to the questions now, and note that the ACS exam, the multiple choice part at least, always has 60 questions, and there's no penalty for guessing. So your goal is to get as many of these right as possible. So let's now begin by looking at number 1. So let me just zoom in a bit so we can see the question. And here we go. So the very first question says, a reaction mixture is prepared containing 0.6 moles of aluminum. So we can write that down. 0.6 moles of aluminum. I don't know why the text is blurry, but no problem. And 1.2 moles of manganese dioxide. So let's add the sig figs just because, it's up to you, of course, but I always like to keep track of them because it's good practice. And it says the mixture is heated until one of the reactants have been completely consumed according to the equation. So here we have an equation, and we're going to use this to answer the question. What quantity, whoa, my screen just went that way. What quantity of which reactant remains uncombined? So it's basically asking which reactant remains uncombined and how much of it remains uncombined. So looking at this reaction, we're basically finding the limiting reactant, and that limiting reactant will be completely consumed, leaving behind the unconsumed stuff. So let's figure out what our limiting reactant is. So we know that 0.6 moles of aluminum, well, you can produce half as many moles of aluminum oxide. So you could produce 0.30 moles of aluminum oxide. Now, 1.2 moles of manganese dioxide, according to this reaction, can form 1/3 as many moles of aluminum oxide. So 1.2 divided by 3 is 0.40 moles of aluminum oxide. So guess what? Our limiting reactant is aluminum, because aluminum can produce less moles of product, meaning that it'll run out first. And what does that mean exactly? Well, let's figure out how many moles of manganese dioxide react with aluminum. So 0.60 moles of aluminum react with how many moles of manganese dioxide? Well, for every 3 moles of manganese dioxide, it requires 2 moles of aluminum to completely react to form the products, according to the reaction. And 0.6 divided by 2 is 0.3 times 3 is 0.9 moles of manganese dioxide reacted if all of this reacts. So if all this reacts, we run out of this reactant, and we use up that much, but we had this much originally. So if we use up this much, and we had this much originally, then what we have left over is just 1.20 minus 0.90, which is 0.30 moles of manganese dioxide. And our answer there should be C, as in cat. So let's now do number 2. Let me erase this. And if you need the work, you can always rewind the video, by the way. And let me delete that weird line over there. And let's get started. A solution with a mass of 1.263 grams. So the mass of solution is 1.263 grams, containing an unknown amount of potassium ions. So it contains potassium ions, and we don't know the mass of the potassium ions. Was treated with excess sodium tetraphenylborate to precipitate 1.003 grams of potassium. I'm assuming that anion right there that's bundled with a K plus is the tetraphenylborate, and it tells you the molar mass of this salt we have over here. What is the mass percentage of potassium in the original solution? Well, what insight you basically have to get from this is that we have a solution that's that many grams, and it has an unknown amount of grams of potassium, but it will be treated with tetraphenylborate to precipitate it out. So we're assuming that all of the K in here will be completely taken out. So let's pretend that all the K gets taken out. So all K taken out. And it's taken out because it's precipitated out by reacting it with the anion, which apparently likes to precipitate with K. So we know that we had 1.003 grams of this precipitate. And what we can do is, in this precipitate, there's that certain amount of K in it. That's the amount of K that got precipitated out, because all of that precipitate has, all the K that it precipitated out. I don't know if that really makes sense, but basically, this 1.003 grams within it contains that K that you originally had in the solution, and we want to find that. So how do we find the moles of K in the solution originally? Well, we have the grams of that salt, and within that salt we have the potassium. So let's write a little conversion to convert our stuff to moles of K. So we have 1.003 grams of the salt, and the salt has a molar mass of 358.33 grams per mole of salt. And looking at the salt's formula, we can see that for every 1 mole of salt, or 1 formula unit of salt, we have 1 K. So we have 1 mole of K plus, more specifically, because it's salt. So we'll get the moles of K, but I kind of want the grams of K, because within that 1.003 grams of this stuff, there's a certain amount of grams of K within it. And we want to find that amount of K because that amount of K was in the original solution. So we can use the molar mass, of course. And the molar mass of K plus is basically equal to the molar mass of K because they differ by an electron, and an electron is super duper light. So we kind of just ignore the fact that it's missing an electron because its mass won't be affected. So according to this table, K is 39.10. We go back to the question, and voila, we have our molar mass, 39.10 grams. Now, chucking this into your calculator, let's do that. So 1.003 divided by 358.33 times 39.1. I got 0.1094 grams of potassium in our original solution. So now I want to find the percent mass. So if our solution was this many grams, and if the potassium was this many grams, and we need the mass percentage of potassium in the solution, and also remember, mass percent is always equal to the mass of the stuff that we're looking at divided by the mass of everything. And in this case, it's just the mass of the stuff, 0.1094 grams of the K plus over the mass of everything, which is the solution, by the way, because the solution consists of the solute and the solvent, which is everything. And doing the math, and of course you have to multiply by 100% to make it a percent. So divide by 1.263, converted to percent, I got 8.67%. And look at that. We are done with this question, actually. So the answer is A. Alright, let's do number 3 now. So let me erase all this stuff, because number 3 is going to require quite a bit of space. Number 3, so let's see, that's number 3. A typical polyethylene grocery bag weighs 12.4 grams. How many metric tons of carbon dioxide would be released into the atmosphere if the 102 billion bags used in 1 year in the United States were burned? Now, you wouldn't want to do that, honestly, because that's bad for the environment, but it's super theoretical, so let's figure this out. What exactly are we looking at? We're burning polyethylene grocery bags, but what is polyethylene? Well, oh my gosh, I don't know what that is. Let me undo that. Seems like my sleeves created some artwork back there that we don't really need for this problem. So we are looking at this problem and we're thinking about what polyethylene is. Well, polyethylene is simply just ethylene connected to other ethylenes. Because if you remember, polyethylene is a type of plastic, and if you didn't get that, a grocery bag is usually made of plastic, and plastics are polymers. They consist of many monomers, and in this case our monomer is ethylene. And what exactly is ethylene? Well, ethylene is C2H4. It's also called ethene, and it kind of looks like this. And another name that you should know or recognize is acetylene. And this simply is just this. Can you guess the formula? Yep, C2H2. So these are the two weird names that are pretty common, and it's something that you should probably know. So now that we know that, let's erase that, and let's figure out the problem. So it's saying it's burning polyethylene. We can just think of polyethylene as just a bunch of ethylenes, and those amount of ethylenes add up to 12.4 grams. So before we start, let's write a reaction showing the burning of ethylene, because burning polyethylene is like burning ethylene connected together. Same idea. So ethylene is C2H4, and we don't need any states. It would be solid, by the way. and it reacts with oxygen gas to produce CO2 and water. And when I balanced this out, I got 3 oxygens, 2 carbon dioxides, and 2 waters. Let's see if the atoms balance out. 2 carbons, great. 4 carbons, 2 carbons, 6 carbon, what am I saying? 2 oxygens, 4 oxygens, because 2 times 2, plus 2 more oxygens is 6 oxygens. On this side there are 6 oxygens, that's great. 2 times 2 is 4 hydrogens, and 4 hydrogens. So this reaction is balanced. Now I can continue. Let's figure out how many moles of ethylene are in 12.4 grams of ethylene to figure out, how many grams or moles of ethylene are there in 102 billion of these bags. So each bag, so let's write a bag. Well, actually, let's put that on the denominator, because you usually want to put the stuff that you want to find on the numerator. 12.4 grams of, ethylene per bag. And this is multiplied by the molar mass of ethylene. And some common molar masses you should try to memorize is carbon is 12.01 grams per mole. Hydrogen is always 1.01 grams per mole. And when you do the math, 12.01 times 2 plus 4.04 times, got my math ahead. I'll just write it out, 12.01 times 2 for, 2 carbons plus 4 hydrogens times the molar mass of each hydrogen, 1.01. And doing the math, well, let's see what the math tells us. It tells us that the molar mass of C2H4 is 28.06 grams per mole of C2H4. And I'll label these so that we can figure out what our units are by the end of this. So let's continue on. And we figure out from this that 12.4 divided by 28.06 gives us about 0.44191 moles of C2H4 per bag. And I kept extra sig figs, so I'm going to keep track of my sig figs, even though it's not really relevant since the problem doesn't require you to know sig figs since they only want the number. So let's continue. It says there are 102 billion bags. So 102 billion. A billion is 10 to the 9 bags. And we'll figure out how many moles of C2H4 we're burning after this. So we're times 102 times 10 to the 9. And that gets us a lot of moles of, C2H4. 507. Let's put our sig fig indicator there, times 10 to the 10 moles of C2H4. Now, let's look at the reaction. It wants us to find how much carbon dioxide would be released. So we want to see how much moles of carbon dioxide would be released by burning this amount of moles of, C2H4. Well, this reaction says for every 1 mole of this, we have 2 moles of CO2. So we can write a conversion there. 2 moles of CO2 for every mole of C2H4. Notice how the moles of C2H4 cancel out just like that. So we're multiplying this by 2. We get 9.01. Well, let's do 9.015 times 10 to the 10 moles of carbon dioxide. And it seems like it wants the metric tons. So we're going to have to do a little bit of conversion to get there. Now, tons is a sort of weight. So we've got to convert moles to grams first before doing anything. Now, the molar mass of carbon dioxide is going to be 12.01 plus 16 times 2, which is 32 plus 12, that's 44.01. So 44.01 grams of carbon dioxide per mole of carbon dioxide. And let me use an eraser to erase this. And we're not done yet. We know we have that many grams of carbon dioxide, but we want metric tons. And it says 1 metric ton is 1,000 kilos. So I want to convert the grams to kilograms. So we know that 10 to the third grams is 1 kilogram. And I put the grams on the bottom to cancel the grams at the top, because we want to cancel out things when we set up stuff. And then we can use that conversion, saying that 1,000 kilograms is in 1 metric ton. I don't know if that's right units for it, but the point is, our units cancel out. That's like the most important thing here. And we end up with basically metric tons of carbon dioxide once we do this. So we're going to multiply by 44.01 divided by 10 to the third divided by 1,000, which is 10 to the third. All right, I got 3.97 times 10 to the count your decimal places 6 metric tons of, well, that's not even a T, carbon dioxide. What answer choice is that? Well, it seems like C is our answer, and I was 0.01 off. Who cares? It's probably just rounding error, but the answer is C. So let's take a look at Dooning. These problems, as you notice, take a while, and usually that happens because on exams like these, especially on the national portion, the first questions are usually very laborious, so don't be surprised. Number 4, which mixture of water and sulfuric acid represent a solution with a concentration that's closest to 30% by mass, H2SO4? What an interesting problem. So let's figure out the percent mass of A, because there's really no way to do this without doing all of them, unless you are just very insightful. So 30 grams of H2SO4, and remember, 30% by mass means 30%. Okay, so mass percent is mass, in this case, mass of H2SO4 over mass of everything. In this case, it's just a mass of solution. So the mass of the solution is not 100 for A, it's 130. And the reason being is that the solution is made up of the solvent and the solute. So you got to combine those two. And let's multiply by 100% in our brains. 30 divided by 130 is 23%. Not very great. Let's see what B is. 1 mole of H2SO4. Oh, now we're dealing with moles. So we got to find the molar mass of H2SO4. So back to our periodic table. So here's our periodic table. Let's figure out the molar mass of H2SO4. So I kind of care most about the S, because that's the most uncommon thing. Well, do this, H2SO4, it's 2 H's, 2 times 1.01. Now let's do the oxygens, and the S is 32.07. The molar mass of this stuff is 2 times 1.01 plus 4 times 16 plus 32.07, 98.09 grams per mole. All right, 98.09, here we come. We're going to shove that right into that question so we can figure it out. So, 1 mole of H2SO4 is 9. Okay, I should always make sure that that doesn't happen. 98.09 grams and plus 200 grams of water. So, this setup that I'm going to do is, well, 98.09 grams of the H2SO4 over the grams of solution, which is just, the grams of solute plus the grams of solvent, since those two make up the solution. So 298.09 grams, and that will kind of lead you to, let's see, 298.09. That's 32.9%. I think that's pretty close. Let's check out what C is. 30 moles of H2SO4. So let's convert that to grams. 30 times 98.09 gets us 2942.7 grams. Notice how I'm ignoring sig figs, and that's because it's kind of irrelevant in this problem, unless you really want to. And this is just 700 grams of water. So in this case, we're going to do this, 2942.7 grams of H2SO4 divided by the grams of solution, which is just these two added up. So that number plus 700 is 3642.7. I can tell you immediately that this is going to be like 80% at least. Well, maybe less than that, but around there. Let's do the math. I got 80.8%. No, this is definitely not right. And so far, B is closer to 30 than A is. So let's figure out what D is. So now it's going to be moles of H2O. So let's find the grams of H2SO4 first. 0.3 times 98.09. That's 29.43 grams. 0.7 moles of water. Water is 2 times 1.01 plus 16. That's going to be 18.02 grams per mole. So 0.7 times 18.02 is 12.61 grams of water. Now let's figure out the mass percent. 29.43 over, whoa, that's not right. 29.43 over, these two added up. So let me add up this for you guys. And I got 42.041. So divide these two, 29.43 divided by 42.041, I got 70% essentially. Nope, and I think B is the answer for that question. And hip hip hooray! We're 4 problems into the thing, and it's been a while. Not to worry, these questions that follow might be a little bit faster. Number 5. How at the freezing point depression of a 0.05 molality, I don't know, I think it's molal, I don't know. But in the end, this is molality, so I'll call that 0.05 molality. Calcium chloride solution compare with that of a sodium chloride solution. So when we're looking at freezing point depression, we don't care about the molality of the salt, we care about the molality of the particles. How to get the molality of particles? That's the I value of the salt times the molality of whatever we have. So in this case, it's CaCl2. So guess what? The molality of the particles is what truly determines the freezing point depression. The freezing point depression is the change in the freezing point is equal to the, it's like the freezing point constant or whatever you call it, times the molality of the particles. And you might commonly see this as the molality of the salt or whatever you have times the I value. So you see how the higher the molality of particles are, the larger the change in freezing point. And since it's freezing point depression, our freezing point is going to go down. So where we start 0 degrees Celsius, and it's just going to go down from there. So that change is going downwards, by the way. And let's see. So the higher the molality of particles, the more change in the freezing point we will have, the lower the temperature will be. So basically, the higher the molality of the particles, the more depression the freezing point will experience. Not psychologically, but depression as in going down. So, which one will have, well, we're not comparing it. Let's read the question. So, the molality of the particles for calcium chloride is just 0.05 times 3, 1 calcium, 2 chlorides. That's 0.15 mole out of, particles. Now, how it compared without a sodium chloride solution, that's an I value of 2, by the way. So, the higher the molality of particles, the more depression there will be. So, let's figure this out. Would it be less than that for 0.1 molality of sodium chloride? Well, 0.1 molality of sodium chloride is 0.2 molality of the particles. So, it looks like the depression caused by 0.1 molality of sodium chloride will actually be greater than the depression caused by the 0.05 molality of calcium chloride. So it looks like it's true. Yeah, the freezing point depression for that will be less than this because this has a higher molality of particles, and that leads to more depression for this one. So yeah, this one will have less than this because the molality of the particles for calcium chloride is 0.15, while the molality is a lot greater here, which means more depression here, so that's less than this. It looks like A is our answer, and I'm not going to look at the others because They're all basically just extensions of this problem, but with like way more molality, and we know that way more doesn't matter because it's not going to be between 0.1 and 0.2, because we already know it's going to cause a depression that's less than this. So let's stick with A, and that's one type of problem that should be super fast to solve if you know what you're doing. So let's look at number 6. What's a mole fraction of CH3OH in an aqueous solution that is 12.0 molality in CH3OH? Now, what's CH3OH? Well, CH3OH kind of looks like that if you're a little bit curious. And that's methanol because there's one carbon. And we use methyl to ascribe that. So let's figure this out. Well, there's just a bunch of lines everywhere. Let me just undo all that for a second. Yeah, let me just undo that as well. So I'm able to undo all those lines that I created. Okay, that's not that bad. Alright, let's just do the problem. 12.0 molality. So molality, remember, is just moles of the solute. In our case, it's methanol, or CH3OH, over the kilograms of solvent. And in this case, it's for every 1 kilogram of solvent, and it's aqueous aqua water. There you go. So mole fraction, well, the mole fraction of CH3OH is simply the moles of CH3OH over, guess what, the moles of everything. And the moles of everything is just the moles of CH3OH plus what other thing is in there? Well, there's water. And let's solve this. So 1 kilogram of water is 1,000 grams of water, which, if you divide by 18.02 to the molar mass, you get 55.49 moles of water. Now, I'm not even focusing on sig figs at this point. Even though it should have 1 sig fig, technically. Well, actually, no. This is an exact number because it's the definition. It's for exactly 1 kilogram of water, so there's technically no sig figs on that. But why am I even talking about sig figs when it doesn't matter in multiple choice, right? So moles of CH3OH, that's 12 divided by 12 plus 55.49. Doing the math, I got 0.178. That's A. So let's continue on with number 7. Number 7 says 3 different oxides of nitrogen, so nitrogen oxides. And looking at the wording, it's anything that has nitrogen and has some oxides or some oxygens. So the formula will be NXOY. And we have to figure out what X and Y are. This is an empirical formula problem. Whoa. Alright, there you go. So 3 different oxides of nitrogen each contain 7 grams of nitrogen, so they all contain 7 grams of nitrogen, and they weigh 15 grams, 23 grams, and 19 grams, respectively. So we're going to follow that order when answering the questions. What are their empirical formulas? Well, let's figure this out. So they all have nitrogen. Now, the only difference is that, well, they have different amounts of oxygen. So if a nitrogen oxide weighs 15 grams and it has 7 grams of nitrogen, how many grams of oxygen would it have? Well, the remaining 8 would be oxygen. So for number 1, the first one in our list, it's going to be 8 grams of oxygen. What about the second one? 23 grams of substance. If 7 of those grams are nitrogen, then 16 of those grams will be oxygen. Number 3, 19 minus 7 is 12 grams of oxygen. And let's convert these all to moles now, because that's what we need to do in order to find the empirical formula. So 7 grams of nitrogen, the molar mass of nitrogen is 14.01. Since this is multiple choice, we're not concerned with accuracy, so we could just, round this as 7 divided by 14, which is 1/2 moles of nitrogen. And so let's just split this up so that it's a little bit clearer. This is divide by 16, because that's more mass of oxygen. 1/2 moles of oxygen. This is actually 1 mole of oxygen. And this is 3/4 moles of oxygen. Alright, so let's now find the empirical formulas for each of these. So, the first one has this many grams of nitrogen and this many grams of oxygen. So, we're going to look at these two first. So, we divide both by 1/2 and we get a 1-to-1 ratio. So, the first substance is just NO. No. Alright, number 2. That's our second substance. Second substance has this many moles of nitrogen and this many moles of oxygen. Now divide both by 1/2 because we have to divide by the smallest one. So 1/2 divided by 1/2 is 1. 1 divided by 1/2, we're going to divide by 1/2 here to get like whole numbers. So, that's going to be 2. And the second substance is going to be NO2. Now let's look at the third substance. Let's divide everything by 1/2 again, because that's the smallest. 1/2 moles of N and 3/4 moles of O. And, we've got to find the ratio between N and O. You might figure out without even doing the math, but we're going to do the math, because that's the best way to do it. 1/2 divided by 1/2 is 1. 3/4 divided by 1/2, well, I don't know. From the top of my head, I think it's 3/2. Let's do that. So, yeah, I got 3/2 actually. So you can't really write formulas like that. You gotta make them whole numbers. So let's multiply both of them by 2 to, expand this ratio so that it's a ratio between whole numbers and not decimals. So you get 2 to 3, and guess what? Our second one is N2O3. So what are the three? NO, NO2, and N2O3. NO, NO2, N2O3. That is A. Great job. Now, at this point, I forgot to say it, but if you didn't do this test beforehand, the 2013 national exam, I highly recommend you do it. And, to experience the problems for yourself before, looking at the answers. But if you really want to just look at me do the work, and if that's how you learn, well, go for it. I have no objection against it. So let's erase this stuff. So I don't know why the eraser tool is not working. There you go. Erase. Let's erase everything. So I'm erasing some stuff accidentally. So let's actually undo that, because I don't want to erase stuff that I don't need to erase. So hopefully half of this video isn't me erasing. That would be pretty bad. Right, looks like I've done enough erasing for today. Well, for now, actually. Let's look at number 8. Which substance is used in self-contained breathing equipment because it absorbs exhaled CO2 and water and releases O2 gas? Now, this problem is a little bit crazy, and I could agree with you no less, because it's kind of that random problem that just gets you. And in this case, you kind of just gotta guess. So, what's the best way to guess? Well, you kind of know that when you mix sodium hydroxide and water, nothing really happens. You don't produce O2 gas. So C is out. Lithium oxide and water, actually, if you learn this, will produce hydroxide because of the nature of acids and bases, where the O2 minus will react with water to, it'll basically drag out an H and it'll form 2 OH minuses. But we're not there yet. I mean, if you know that, awesome. But basically, D is not the answer. So you have B and A. Na2O2, that's just, so this must be O2 2 minus. That's a peroxide. This one, O2 minus, is a superoxide. Now, honestly, these two answers are kind of low-key similar, and you don't really know what the true answer is. But if you listen to the names, super sounds more awesome, and it's awesome because it can be used in self-contained breathing, so A is our answer. Now, that's really not the right way to do it, but you should cancel out C and D because you know that those don't create O2 gas. Now these two, well, it's up to guessing, and this is one of the problems where you know it or you don't, and it's kind of luck too. Let's take a look at number 9. This one requires a little bit of knowledge. A sample of white solid is known to be sodium bicarbonate, silver nitrate, sodium sulfide, and calcium bromide, which 0.1 molar aqueous solution can be used to confirm the identity of the solid. So 0.1 molar should be reminiscent of precipitation. But there's a lot more going on in this problem, and I'll show you how this works. So let's think about this and see which one of these can distinguish between them. Now, if you test out NH3, you'll figure out that you can't really distinguish anything. Now, if you test NaOH, you'll figure out that you won't be able to distinguish between these two because, adding OH doesn't really do anything since they both share sodiums. So we want to add something that affects, the anion more. So in this case, let's look at KCl. Now, what does KCl do for us? Well, I don't know. Well, I know that Cl can be used to precipitate out silver chloride, but you can't really use potassium chloride to distinguish these two because it doesn't precipitate any of these two, since chloride doesn't precipitate with sodium and potassium doesn't precipitate with these two. So when you think of mixing stuff, you want to think of the ions matching with each other and whether they will precipitate. So in this case, the Cl matched with the Ag+, and it precipitates. But if you can't distinguish between these two, what's the point, right? So the answer is B, and I'll show you why. How do you distinguish between these four? Well, HCl is an acid. When you add an acid to HCO3 minus, so this is an H+, that's what an acid is, you actually get CO2 plus H2O, because this actually produces H2CO3, carbonic acid, which naturally decomposes to these two stuff. So mixing this with this will get you some gas. Hey, we are going somewhere. And adding the Cl and the Ag will precipitate AgCl, silver chloride. So that's, well, why am I writing B? Let's just write substance 2. So substance 2, if it precipitates something out, it's going to be this guy. If it produces gas, it's going to be the first one. Now, what about sodium sulfide? Well, guess what? 2H pluses plus S2 minus actually gets H2S, gas. And this has a character odor to it. So that helps you distinguish it between carbon dioxide and hydrogen sulfide, I think. So this is also a gas, and we're learning a lot of cool stuff. And if you already knew this, good for you. And calcium bromide, well, let's be honest, nothing's going to happen. So if nothing happens, it's 4. And that's how you distinguish between these 4 substances with just HCl. Pretty awesome, right? So number 9 is going to be B. So let's do number 10 now. The infrared frequency. Whoa, wait a second. Do we even know what that is? Well, you do learn in organic chemistry, but probably not in a general chemistry class like AP Chem. The CX vibration, so CX is the bond vibration, for CH3X depends on which of the following. Well, vibration is the bond, vibrating. So you can think of vibrations as, some kind of frequency. So it'll vibrate up and down, up and down. But the answer choices are kind of weird. Does it depend on the mass, the strength of the bond, or the type of bond, the stretch or bend, whatever that is, right? So to tell you the truth, this problem, unless you know what's going on and you're really knowledgeable, requires some guessing for the average student. So for these types of problems, you want to think kind of common sense. Now, what would cause the bond vibration to change? So the infrared frequency, the rate at which it goes up and down, what would change that? Well, the strength would change it because something that's stronger might, vibrate less because it's more tightly bound.
Now, I think 2 is right. Now, what about 3? The type of vibration, stretch, or bend. Sounds right. The mass effects, does the mass really matter? Well, maybe if it's a higher mass, it has more protons. Well, actually, no. If it has a higher mass, doesn't that mean it's bigger? And does that mean that, like, the electrons are more toward the outside? And I don't know. I mean, I don't know if the mass effects would affect it, but maybe it does, because the bond is farther away from the nucleus since the mass of X is larger, maybe that causes the bond to be a little bit weaker. Because remember, bonds are the result of electrons being attracted to each other's, nucleus, and that's what creates a bond. It's when electrons are attracted to, the nucleus of each of the atoms, and that's what creates a bond. So maybe it does matter, and maybe the answer is D. And my logic might be completely flawed, but the answer is D according to the answer. So the answer is D. And my logic might work, maybe it won't work in some cases, but you want to use logic in those cases to solve those types of problems. Let's take a look at 11. When the permanganate ion, MnO4- acts as an oxidizing agent, it forms different products depending on the pH. Which species corresponds to the conditions listed? So for this problem, I want all of you to do a little bit of elimination. So for this problem, you basically know it or you don't, let's be honest. And if you don't know it, there are a few ways to figure this out. You can figure about by looking at these choices, and you're like, well, 3 of these choices have Mn2 plus as their option, so C's probably not the answer, unless they're being super savvy, but they're probably not. Now, if you look at this, you can kind of eliminate this because you see that MnO2 manganese dioxide is pretty common. We're left with these two. Now, they're equal in frequency, so we're in a bit of a pinch. Now, from this point, it's kind of guessing. But is it, though? Let's see. Let's find the oxidation number. That's +2. The oxidation of this is +4. So let's order this acidic to neutral to basic. So +2 +4. So what's this? That's +2. Kind of suspicious, don't you think? But this one, MnO4 each O is -2, so -8 +6. So will equal the charge. So MnO4 the Mn has a +6 oxidation number. And that looks more right because notice how as you increase in pH from acidic to basic, the oxidation number increases like a pattern. And when we see patterns, we like patterns. So because I like patterns, I'm going to choose B. And guess what? That's the right answer. So sometimes you just got to use some logic to solve these problems, and it goes a long way, let's be honest. No, whoa, number 17. We're not even on number 12 yet. Let's look at number 12. So number 12.
In an experiment to verify the value of absolute zero, by the way, isn't when K is equal to 0, a student is instructed to measure the volume of helium in a 10 milliliter syringe at 10 degrees Celsius intervals between 0 and 100 degrees Celsius. She is told to plot the volume versus temperature and to extrapolate, which means to kind of extend this graph to 0 volume and read the resulting temperature. Which modification of the experimental procedure will give the best value for absolute zero? So let's figure out what exactly is going on. So we know that the ideal gas law equation is PV equals nRT. It seems like there's a sample of helium with varying amounts of volume and varying temperatures. So the volume and temperature are changing. And we can assume that the volume of helium, that sample of helium we have will stay the same. So the moles of helium will stay the same since we're not changing the sample. So this is a constant, that's a constant. And the pressure. Now, technically, if you're comparing only these two, the pressure should be constant. And since it is in a syringe after all, what the syringe will do, so we can think of a syringe as kind of like a piston, but it's a syringe. So it kind of looks like that, and you have the gas. And what ends up happening is that if the gas inside is 1 atmosphere in pressure, and the pressure outside is also 1 atmosphere, well, don't you think they cancel out? And in the end, you get this equilibrium where the piston doesn't really move. Now, what ends up happening is that this pressure will always basically stay at 1 atmosphere for the gas because the outside will always push down until it equalizes with the inside. So maybe if the inside is 2 atmospheres, then if the outside is 1 atmosphere, then this piston will push up. And as the gas expands, its pressure will decrease to 1. And once it's equal to the outside, it'll stop pushing because the pressures on each side are equal. So that's kind of how a piston works. And you can kind of assume that the pressure will stay constant because it will do it itself. So for example, this is the piston, and pretend that you heat this thing up. If you heat this up, the pressure will go up. If the pressure goes up, that extra pressure will kind of push this piston up. And as it pushes it up, the volume increases, which decreases the pressure until it's equal to the 1 atmosphere, which is the external pressure that we experience at sea level. So that's kind of the context of the problem. Don't know if I had to go that much into it, but I think it's important. So let's set this up. We can figure out from this that V over N, so I'm dividing, well actually no, I don't want to divide by N. I want to divide by T because I want the two variables that are changed on one side. And these are my constants, and like that. And then since all of this is considered constant, you can just call that a K. So notice how volume over temperature is a constant. So that means that volume and temperature, well, we can rewrite this as volume equals Tk. And that's something called directly proportional. And that means that when you draw the graph with T and volume, it'll form a straight line that goes straight through 0, 0. And basically, it's going to kind of look like that. Now, what this person wants to do is that the person wants to graph, between 0 and 100 degrees Celsius. So what we could do is that we'll call this Kelvin, and we can change all this to Kelvin by saying negative, oh, no. 0 degrees Celsius is 273 Kelvin, and 100 degrees Celsius is 373 Kelvin. So basically, let's just graph that. And what they want to do is that they're going to vary this temperature from 0 to 100 at 10 degrees Celsius intervals. And what's going to happen is that as you graph these temperatures, what's going to happen is that it's going to form a line with respect to volume, since volume and temperature are directly proportional. So when you graph it, it'll kind of look like that. And that's like between 273 and 373, which is what's going on in the experiment. And it wants us to extrapolate this to 0, 0, which is 0 volume and 0 Kelvin. And that's how we estimate absolute zero. So pretty cool, right? But that's not the question. The question wants us to modify this procedure to give the best value for absolute zero. So let's kind of erase this, and we kind of know that the points will kind of like form a line. So maybe it'll look like that, but it will eventually form a line that looks like this form where y equals mx, which is directly proportional. So what does A say? Correcting each measured volume to 1 atmosphere pressure before plotting. Now your syringe that you have is technically self-correcting since the piston will move up and down until the inside is 1 atmosphere. That's just how they work. So you don't need to correct each measured volume for 1 to 1 atmosphere when the volume is already at 1 atmosphere. Doesn't really make that much sense. Doubling the number of temperature volume values between 0 and 100? Possibly. I mean, if I have more points, that will give me a better line. But like, in the end, I feel like that's not the best way to do things. And this one is a question mark. Using a thermometer that can measure temperatures that are accurate to 2 sig figs, I'm thinking. Well, maybe. I mean, if you measure to the plus or minus 0.10 instead of something like plus or minus 1, I mean, yeah, you could potentially have a more accurate measurement. But does that really matter? Does like the difference, does a 0.1 difference versus a 1 difference really matter? We'll see. But our goal is for us to make a line from the points in the data so that we can connect it and extrapolate, which means that going beyond the values we have to find this point right here, which is what we want. And that would allow us to find basically absolute zero. And ideally, it would cross that place. And, sometimes the line won't be perfect, so maybe it'll go a little here, and then you would get like a measurement for K that's like not absolute zero. But if you do the experiment right, it should be around absolute zero, which is always 0 Kelvin. Now, what's the last one? Measuring the volume of helium in the syringe at -40 and -80. So we're kind of going like in this region, and we're kind of measuring the volumes at those temperatures. So we're going to have some extra points. And note that this is at low temperatures, so gases start deviating from the real gas law. But since this is helium, and helium is super duper small, then it's kind of called an ideal gas. And it's an ideal gas because it's small, and it doesn't have that many intermolecular forces because it doesn't have any polarity. It's super small, no attractions. So this is pretty ideal. And remember, an ideal gas is something that's super small. Like, we don't even count its volume. And since helium is super duper small, since it's the second element on our periodic table, it can be considered an ideal gas. So even if we lower the temperature, it'll still be an ideal gas. So it is appropriate to do this. And what's good about this, so we get extra points. And we like extra points because it makes our line more accurate. Let's just say we had like all these points pointing like a line that's going that way. But what if we're graphing these points and it shows that, maybe it's like here and maybe we have to shift the line. So notice how by having these extra points, it's super helpful in drawing that line and extrapolating it to 0, 0, ideally. I mean, it won't hit that, but it will hit close to that, and having more points that are along this line will help you do that. So rather than having points here is more helpful because it tells you kind of the direction in which the line's going. So D is actually the answer here, and that took a while to explain, but I mean, it's a hard problem to be honest. So let's move on to number 13. Hopefully it's a little bit easier. Number 13, the Henry Law's constant for oxygen gas is 1.3 times 10 to the negative 3 molar per atmosphere. What is the partial pressure of oxygen gas above a solution at 25 degrees Celsius with an O2 concentration of that? So Henry's law basically says that if you have some kind of gas over, in this case, water, then that that gas, some of it will dissolve inside. And the interesting thing is that the amount that dissolves, so I'm going to call M the amount that dissolves, is equal to a constant times the partial pressure of the gas. And it's directly proportional, as you can see. So as this increases the partial pressure of the gas, the more it will dissolve. So let's just use this formula to figure out what's going on. So notice how atmospheres to the negative 1 is the unit. So atmospheres will be on the bottom. So our K will be 1.3 times 10 to the negative 3 molar per atmosphere. Now, if we're given the molarity, so our molarity is right there, 2.3 times 10 to the negative 4, notice that we have to multiply this by some kind of pressure so that the pressure will cancel out with the atmospheres to get, well, molar, which is left over. So make sure your units match up when you do this. And sometimes they like to flip the K so that atmosphere is on the top and molarity is on the bottom. And all you would do there is just move it to this side so that the molarities would cancel out. But in this case, the atmospheres cancel out. So what you're going to do is you're going to divide both sides by 1.3 times 10 to the negative 3. And notice how cool this is, because what ends up happening is that the molars cancel out, and you get the partial pressure of O2 just by doing that. 2.3 times 10 to the negative 4 divided by 1.3 times 10 to the negative 3. I got a partial pressure of O2 is equal to 0.18. And that looks like B to me. So for number 13, it's actually B. Now, does this make sense? Well, yes, because if you look at this, it says that for 1 atmosphere, it can dissolve this much stuff. So for this much stuff, how many atmospheres is it? Well, it's kind of proportional if you think about it. Since this is less than this, then the amount of atmospheres that, it's above the solution should be less than 1. And if that doesn't make sense, just refer to this, because that's probably the most helpful one out of all of them. Now it's number 14. 14 is going to be interesting, but not so bad actually. Sample of gas measured at 20 degrees Celsius and 4 atmospheres is heated to 40 degrees Celsius. So we can 20 degrees Celsius, 4.0 atmospheres. It's heated to 40 degrees Celsius. Now what I always like to do is just change it to 273 to 93 Kelvin. 40 becomes, I think, 313 Kelvin. And that's the transformation. We're focusing on the Kelvin since we use Kelvin when we're doing the math. I'm not Celsius, usually. Now, it's at a constant volume. So, we know that there's a constant volume and the sample of gas is constant, so N is constant as well. And if we use PV equals nRT, we know that V and N are constant, and of course R is a constant, so P over T is equal to nR over V, which are all constants, so you could call that a K. And you get that P equals KT. And what you could do from there is you could kind of reverse engineer this to say P over T equals K, and thus pressure and temperature are proportional according to this. So P1 over T1 is equal to P2 over T2. Now, if you notice that, they both should be equal because they both should equal the constant, no matter what pressure or what pairs of pressure and temperature you have. Now, that sounds complicated. Just focus on this one. And basically, it's saying that at a constant volume and moles, if you change this to this, what will happen to the pressure? Well, what will happen to the pressure is that you can think of it this way. 313 divided by 293 is just you're multiplying by 1.068. And since we proved that P and T are directly proportional, that means that if the temperature increases by that factor, the pressure should increase by that factor. So 4 times 1.068 will get you 4.27 atmospheres. Now, why am I solving this? Well, you'll see that it's really helpful. Which statement is or are true of the gas after heating relative to its initial state? So after you heat this, so we're just going to draw this, super helpful to draw. So let's draw a container with a constant volume, and it's going to have some gas in it. And what's going to happen is that the temperature is going to go up. So we can kind of draw that change from before to after by, drawing some arrows. So at first it's not going very fast, but by increasing the temperature, the particles move a lot faster now because they are at a higher temperature. They have more energy. Now let's look at our choices. It wants us to talk about which statements are true. Number 1, the average molecular kinetic energy is increased. Well, the definition of temperature is the average molecular kinetic energy, and if that increases, well, this is going to increase too. So 1 is right. 2, the average molecular speed is unchanged. I don't think so. At a higher temperature,
particles have a higher kinetic energy. And remember, kinetic energy is just moving energy. The more moving energy you have for a constant, mass, the faster you're going to go, because kinetic energy is 1/2 mv squared, and that's from physics. Constant mass, if you have more of this, by default, the velocity will also increase. So at a higher temperature, we know that kinetic energy is going to increase. So given, we have constant amount of gas, yeah, the velocity is going to increase as well. And you don't even have to go this far. You know that as temperature goes up, particles move faster. So you know this is not true, because the speed is not unchanged, it's changing a lot. What about this? The pressure of the gas has increased to 8. Well, no, we said it increased to 4.27. So 3 is wrong. And they try to trick you by, doing degrees Celsius, because you might think, that's times 2. So because pressure and temperature are directly proportional, maybe it will double as well. And that's not right, because we got to do Kelvin. Remember that. 4. The number of molecular collisions per second is unchanged. Now, what are molecular collisions? Well, they're basically collisions of, the molecules with other molecules, and especially the wall. Now, particles move faster. Won't they have the opportunity to hit the walls more often? Like, pretend before you can only hit the wall once per second. Maybe this particle, having higher temperature, can hit the wall twice per second. So increasing temperature will increase the number of molecular collisions. So it's not going to remain unchanged. So your answer is just A there. Now let's do number 15. Under what conditions does the behavior of real gases deviate most from that predicted by the ideal gas law? Now, this is kind of memorization, but things deviate at high pressures and low temperatures because these two conditions cause gases to be closer to liquids, if you kind of remember that. Because at a higher pressure, here, how do I put this? So we think of our phase change diagram, right? Kind of looks like that. That's our solid, liquid, and gas. I don't know, maybe it's like, and it doesn't matter. This is a relative shape. Notice how if you go at a higher pressure, so this is pressure and this is temperature, higher pressure will lead you closer to liquid. Lower temperatures will lead you closer, well, to liquid as well. You can think of it like this, like gas is here, lower temperature will lead you closer to liquid, higher pressure will lead you closer to liquid as well. So the closer you are to liquid, the less gas-like you are, and that's why the answer is B. Now there's a more complicated answer which involves the volume not being the actual volume, but let's not talk about that. Basically, if you want to actually know more about that, check out my videos about gas laws, which is, I don't know what unit, it's the unit about gases. And yeah, I mean, if you're curious, check it out. If not, let's continue. Number 16. 1.25 liters of liquid nitrogen with a density of that is vaporized. What volume does the resulting gas occupy at 25 degrees Celsius and 5 atmospheres? So, basically, we have pressure, temperature, and we gotta find volume, but we don't have moles. But wait a second, we do have moles. We have the moles of liquid nitrogen because we have the density, and the density gives us the mass, which we can convert to moles. So here's how it works. 0.25 liters of liquid nitrogen. So liquid nitrogen is just N2. And if you vaporize all of that, well, 0.25 liters of liquid nitrogen will be vaporized. That amount of liquid nitrogen will still stay the same, or specifically, the mass will stay the same. So you're vaporizing a certain mass, and that mass will become the gas that you're going to collect. So you have 0.25 of this. You want to find the mass before doing anything. 0.807 grams per milliliter. Now notice we have a problem here because the units don't match. So why don't I just call this, well, 250 milliliters of N2. Sounds right, right? So doing the math,
we get 250 times 0.807, we got 201.75 grams of N2. So that's the amount of N2, and that's the amount that's going to be in our gas sample. And we convert that to moles by dividing by the molar mass of that, which is 28.02. So divided by 28.02, I got 7.2 moles of N2. Now we can use PV equals nRT. We have moles of gas that was vaporized, and it's at these conditions. So you will be able to solve for volume. PV equals nRT. P is 5.00. Volume is, I don't know. N is 7.2. R is 0.0821. And T is 25 plus 273 is 298. Now let's do the math. 7.2 times 0.0821 times 298 divided by 5. That looks like a 4. Gotta make that a 9. And I got a volume of 35.2 liters. And of course they're following sig figs since this has, that shouldn't have 2 sig figs. Well, actually it does because this original one had 2 sig figs. But why do we care about sig figs? 35.2 is close to 35, which is C. So right there, we just went through a quarter of the test. Pretty brutal, right? Well, not to worry, because it's easier to do this in your head and on paper than to talk through it. And my goal is to talk through it, so it's taking a long time, and I know that, but that's okay. We can do this. Even though the test is hard, we will learn a lot from this, and hopefully it will all work out. Let's look at number 17 now. This one is a little bit interesting, I would say. The phase diagram for sulfur is shown above. Which statement about the diagram is correct? Well, this is a phase diagram. Notice something odd? Well, I noticed something odd. We have 2 solids. How does that work? Well, it just is. So we gotta deal with it. So let's figure out which statement is correct. So given that, we can assume that there are 3 incorrect choices and 1 correct choice. Let's check out A. The critical point is above 154 degrees Celsius and 10 to the 3rd atmospheres. Now, this diagram's really hard to read because everything is blurry. That is not good. So, what I'm going to do is I'm actually going to look this problem up on my phone to get a clearer picture for you guys. So I looked it up, and these are the values. So the pressure is 10 to the 3rd atmospheres. That was a positive 3. And I labeled the rest, but we might not need to use it. So let's check out the first one. The critical point is above 154 degrees Celsius and 10 to the 3rd atmospheres. Now the critical point is actually the point over here where basically once you go at a higher temperature and pressure, you will basically have something called a superfluid. Just kidding. It's the supercritical fluid. And yeah, so over here is supercritical fluid region. And it doesn't look like it's above 154. Well, is it above 154 degrees Celsius? Well, actually, yeah, it is, because if this is 154, then that should be above 154. But is it above 10 to the 3rd atmospheres? Well, this is 10 to the 3rd, and it looks like it's kind of below it. So A is out of the picture there. B, there are only 2 triple points in this diagram. Now, what exactly is a triple point? It's a point at which the liquid, solid, and gas are at equilibrium. Or in other words, equilibrium exists on the line, so we got to find the point in which liquid, solid, and gas all exist, together. And we do that by finding basically the intersection of the curves, where basically that point will touch all 3 regions. So it's actually over here. This region touches the liquid, the vapor or the gas region, and the solid region.
And you might be thinking, what about here? Well, no, because that place over there doesn't touch the liquid. Now, what about here? Not exactly, because it doesn't. This place doesn't touch the vapor place. So we only have one triple point. Unfortunate. C. Monoclinic sulfur is more dense than rhombic sulfur at any temperature. So there's monoclinic and there's rhombic. Now, you could watch my videos or you could just listen to me explain this super quick. So it follows a trend like this, where solid, liquid, and gas. Then basically, this follows the normal trend where the solid is more dense than the liquid, which is more dense than the gas. Now, if you're water and you do this, solid, liquid, gas, and where the curve is kind of inverted over here, then what ends up happening is that the liquid is more dense than the solid, which is more dense than the gas. And the reason, okay, this is just like part of nature, but the reason why this curves up this way is because if you think about it, if we had a solid over here and you increase the pressure, if you increase the pressure, doesn't it want to go to a more dense state? So if it's going to a more dense state, and we know that the more dense state is the liquid, because liquid is more dense than solid, as in the case of water, then naturally, it should go in the liquid region, which is why this curve has to be like this. It can't be like the first one, because if we're at a solid, there's absolutely no way to increase to get, to liquid. And that makes sense because the solid's the most dense thing, and increasing pressure should keep you at the solid level. So that's a really quick explanation, and this seems to follow the normal curve. So we're looking at the boundary between monoclinic sulfur and rhombic sulfur. And by the way, these are just two allotropes of sulfur. So these two things, in essence, they follow the normal pattern. So that means that this is more dense than this. Or in other words, this is more dense than this. So monoclinic sulfur is more dense. No. This is more dense than this, or this is more dense than this. Rhombic more dense than monoclinic. This is saying the exact opposite, that monoclinic is more dense than rhombic. So C is wrong, and D is our answer. But why is D our answer? Monoclinic sulfur forms rhombic sulfur at higher pressures or lower temperatures. Does this make sense? Let's just take a point where monoclinic sulfur exists, and will it turn to rhombic at higher pressures or lower temperatures? Well, at higher pressures, yeah. At lower temperatures, yeah. So you could have just done this by choosing D, because D is the obvious right answer. But of course, we want to go over everything because we need to learn. Let's do number 18 now. Number 18 says, what is the principal difference between crystalline and amorphous solids? Now, actually, the difference between the two is that one is ordered and one is not ordered, so it's D. Now, C and B are out. I could give some counterexamples, actually. Amorphous solids can have a super high molar mass because you have something like, I don't know, butter. Butter is amorphous. Butter is made of a bunch of organic substances that are gigantic, and they have super high molar masses. So, that's a counterexample, and that kind of just disproves the thing. What's this, a stoichiometric solid and a non-stoichiometric solid? Well, that's really unnatural definition of, crystalline and amorphous solids, and that's not usually how you define it. Now, we can find counterexamples where crystalline solids are not actually stoichiometric, and there are a few examples out there. I'm trying to think of one, but I can't. But basically, sometimes you have arrangements of salts that aren't in stoichiometric order. So let me find an example, actually. And I used Google, and apparently Fe0.950 exists, which means that, well, you have a combination of Fe2 plus and Fe3 plus together, and that makes it so that, usually it's like FeO, where Fe is always 2 plus, but if there are 3 pluses out there, you would need less iron ions to cancel out the negative charges of the -2 oxygen anions, so you would need less of them because it's a combination of these two. So that's an example, kind of complicated. Let's not talk about that. Let's talk about A. A says crystalline solids have ionic bonding. Absolutely not true. we know diamond is a crystal, but diamond is just carbon, and carbon doesn't form ionic bonds. It actually forms super strong covalent bonds, and when you try to melt it, what ends up happening is that you have to melt those bonds, or you have to break them to melt it, and it's super hard to break it, which is why diamond is crystalline. It forms a network of carbons called a covalent network, and these are very, very strong. Well, I don't know if they're strong, but they're substances that basically have high melting points. So we just disproved A, and that's why D is right. Now, if you think about diamond, diamond is really orderly. It has these consistent patterns of carbon that branch out forever and ever. So that's why D is our answer. Number 19 says, which are state properties? Now, you might not know what this is, but basically a state property is something where it doesn't matter what path you take to it, because at the end, no matter what path you take to it, it's always the same. So what I mean by that, let's take a look at volume, because that's easy to explain. Let's start at 5 milliliters, and let's start at 20 milliliters. No matter what path I take, as long as it's like an appropriate path, you can always get 10 milliliters. So it doesn't matter what path we take to get to 10 milliliters, because in the end, you have 10 milliliters, and it doesn't matter what path. So state properties are things that don't care about the path in which it takes to get there. So 3 is the correct answer. So we can kind of eliminate A and B. And what about heat? And let's do enthalpy first. Enthalpy, if you watched my videos, is a state property, and that's because each substance basically has a certain amount of heat in it. And no matter what path you take to get to the substance, that substance will still have the same amount of heat. So 1 is correct, and, C is right. But why isn't heat a state property? Well, heat is the transfer of energy, and the transfer of energy depends on what path you take. So if I go from 1 joule to 10 joules, that's a 9 joule difference. That heat exchange is, plus 9. Now if I took a different path of 10 joules, maybe like, I don't know, 2 joules, notice how the amount of heat changes. So the path did matter to getting that final thing. So heat is not a state property. That's why C is our answer. Number 20. This is going to be a long Hess law problem. So we're going to kind of have to do a little bit of erasing. And yeah, let's go and do this problem. So you have a reaction. You want to calculate the delta H naught values from the information below. So this is 100% Hess's law. And what I like to do for Hess's law is I want to arrange everything so that everything's on the right side. So that last equation over here, notice how the HNO2 is on the left-hand side, just like the top. But notice how it's 2 instead of 1. So I want to half this. So how do I half it? Well, I half it. HNO2, half of 2 is 1, becomes half of 1 is 1/2. Whoa. I'm not writing it right. That's right. And then half of O2 and half of water. And I'm not writing states because I don't think there will be the same substances at different states, and it doesn't look like it's the case in this problem, so not to worry. And we could just go a little to the right, and I could say the delta H of this is just half because we halved the reaction, so it's half as much, so it's just 17. And you want to keep in that position because we want that HNO2 to be on the left-hand side. Now take a look at the third one. Now the third one doesn't have anything that's in this. I want to focus on the things that have that main reaction first. I like that second one. That second one has some promising things. Just kidding, it doesn't. What about the first one? Hey, it does. Look at that. Let's half things. They're on the same side, so that's good, but we gotta half it so that it's the same amount. So half NO plus half NO2 plus half Na2O becomes, well, half 2 is 1, so NaNO2. Great, we're almost there. And this has a delta H of negative 427 divided by 2, which is 213.5, I'm guessing. Yeah, that seems legit to me. I mean, you multiply that, it works out. So let's take a look at the third and second one. So looking at this, I know that these two will cancel out because they're not in our final reaction. So we got to cancel them out somehow. How do you cancel something out? Well, you got to put some of the stuff on the right-hand side. And I see some of this stuff over here, but it's on the left-hand side, and we want it on the right-hand side to cancel out with this stuff. So what do? Well, we flip it. And notice how it's only 1/2. So we got to flip and half it. So how do we flip and half it? Well, let's flip it. Let's flip and half it in our minds. So if you flip it, it's going to be 1/2 N2O plus 1/2 O2 becomes half NO2 plus half NO. And the delta H of this one is going to be flipped and halved. So if you flip it, it becomes positive 43. Half it, I think that's 21.5. Let's take a look at the last one. So our last one, let's see, Na2O is on the right side because we want to cancel the left-hand side out, but we got to make it half so that, this is 1/2, this is 1/2, and once they cancel out, we get this brilliant equation at the end. It's just the beauty of Hess's law, I mean, what can I say? So half everything, NaCl plus half water becomes HCl plus half of Na2O. Well, wait a second. The third one had HCl. I don't know why I didn't use it. That's okay. It'll work out. So we halved it. So we're halving 507. What's half of 507? I have no clue. Well, I think I have a clue. It's 253.5. There you go. Is that a 5 or is that a 3? I actually don't know. I think that's a 5. Alright. So let's move on and let's add these delta H's up. But before that, we're going to see if these chemicals cancel out to give that final equation. So our NO2 and NOs cancel out. Bravo to us. And let's see. Our O2s cancel out. Do our waters cancel out? I sure hope so. Does our sodium chloride cancel out? It's not supposed to because it's in the final reaction. I think our N2O cancels out here. And our Na2O will cancel out. So on the right-hand side, it's right there. And we get left over HNO2 plus NaCl becomes, let's see. Wow, that's just a sea of chemicals. HCl plus NaNO2. Bravo to us, we got the final reaction. So all I have to do is add up all these numbers. So 21.5 minus, let's just make that clear, 213.5 plus 253.5 plus 17. You plug this into your calculator to get your answer. Make sure to put in the calculator correctly so you don't get the wrong answer. And I got 78.5. So, okay, 78.5 kilojoules per mole of that reaction. And look at that. It's B. Took a while, but we did it. Let's do number 21. For which reaction is the delta H value close to the delta E value? Now you got to know a special formula for this, because if you don't know the special formula, you kind of can't do this. Delta H is equal to delta E plus, I think delta, no, it's not delta P, it's P delta V. And I remember that there was also delta PV, but, we're going to ignore that. We usually focus on this one. So PV is equal to nRT. So we can do this. Delta H equals delta E plus delta N, we're assuming the change in the moles of gas, RT. So notice how we're changing moles and changing volume. And it's perfectly legal to do this. And you're wondering, how do you solve this? It's energy. And this is not energy. That's like pressure, right? Well, guess what? This R can be 0.0821. We do that for usually things that don't involve energy. Now, what if it involves energy? Well, you use that other one, 8.31 times 10 to the negative 3. And you can kind of match the units, and you'll see that the units will work out because the units for this one will actually be kilojoules per, I think, mole times Kelvin. And you notice how T and moles will cancel at the bottom to leave kilojoules, and that can be added with kilojoules. So, yeah, use this one when it comes to energy. So, that's actually not very important because we want to find when delta H is close to delta E, or in other words, basically when they're equal and when the change in the moles of gas is 0, because that will ensure that these are equal and that will ensure that they're close, right? So let's figure this out. The first one has a change in moles of gas, so there's 1 mole of gas, 3 moles of gas, 3 to 1 is negative 2. I don't think that's 0, so that's not right. Well, number 2. Well, number 2, there's 4 moles of gas, becomes 4 moles of gas. That's like 0 equals a change in the moles of gas. And guess what? That's 0. So delta H will essentially equal delta E, or be very close to it. So our answer for number 21 is actually just B. So, in all honesty, no matter what the N is, the delta H and delta E will be pretty close to each other, and they'll be off by a little. But when the problem says close, they probably mean super close. So you probably don't want to, second guess yourself. Just assume that close means equal in this case. And let's see, you might not know what E is, but basically E is something that has to do with the internal energy of the system, which is kind of different from enthalpy. And they differ by, well, the amount of work. And this has to do with one of the laws of thermodynamics that states that the internal energy of a system is equal to the Q, the heat, plus W work. And, enthalpy has to do with Q, E has to do with internal energy, and work has to do with this, P delta V, the pressure volume work. Now, we're not going to get into this. You could watch the video about the first law of thermodynamics, I believe, and if you want to learn from there, go for it. But if not, let's move on to the next problem. Now, let's do number 22 now. What is the value of delta S? So they give us a bunch of delta S values. They give us a bunch of S values, and we know that we can find delta S by basically taking the sum of our S naught values and kind of just taking the sum of the products minus the sum of the reactants to get the change in the entropy, because entropy, or the change in entropy, is just the final amount of entropy minus the initial amount of entropy. So the final is our products and the initials are reactants. So in this case, we simply just kind of chug it into the formula. So we have 2 iron, 2 times 27.3. And we're not going to care about units since everything is in joules per mole Kelvin. And our answer is in joules per Kelvin, ignoring the moles because, I don't know, you could write moles of reaction, I guess, but they didn't. But that doesn't really matter in our context because we only care about the joules. As long as the joules are the same, we're good to go. And we have 3 of carbon dioxide, 213.8, and we had to subtract this by the entropies of the reactant. So we have 1 Fe2O3 plus 3 COs. So doing the math, well, I don't know, I got, let's see, 2 times 2 is 7.3 plus 3 times 2, 13.8 minus 87.4, and we want to put parentheses because we're subtracting a bunch of things. We're subtracting all of this stuff. So minus 87.4 plus 3 times 197.7. I got a pretty small number. I hope this is right. 15.5 joules per Kelvin per, mole of reaction.
It looks like it's one of the answer choices, which kind of reassures me. So let's see. Let's check out 23. What is the temperature at which the reaction below is at equilibrium? So we're looking at a reaction, we're trying to make it at equilibrium, and they give us a delta H and delta S. That's a dead giveaway to use delta G naught equals delta H naught minus T delta S naught, because notice how they give us two of the three variables. Actually, they want us to find the temperature at which delta G is, 0, because when delta G naught is 0, it's going to be at equilibrium. And yeah, they want to know when will the reaction be at equilibrium at standard state conditions, I'm assuming, because they're not specifying anything. So since this is standard state, we want to make that 0. 0 equals delta H naught minus T delta S naught. So we are basically solving for T here. So we're going to add T delta S to both sides. We're going to divide out the delta S naught. So look at that. That's basically what we have to do. But we have to make sure the units are the same so they cancel out. Kilojoules and joules do not mingle. You gotta change that to kilojoules. So it's just negative 0.145 kilojoules per, mole Kelvin. Kind of hard to read, but you get the point. So it's equal to negative 113 over negative 0.145. And notice how this makes sense, since you should have a positive temperature at the end, or else you're doing something wrong, since we do not have negative temperatures in Kelvin. The lowest you could get is 0, which is absolute 0, by the way. So negative 113 divided by negative 0.145 will get us 779.3 Kelvin. Now, is that what we want? No. They want degrees Celsius. And don't just put D. No. We gotta make it into degrees Celsius. And we do that by, we know that we have to subtract 273, but if you are confused, you can think of it this way. We know that 0 Kelvin is negative 273 degrees Celsius. So to get from Kelvin to degrees Celsius, subtract 273. And if you want to be specific, it's 0.15. But we're not going to be that specific. So we just subtract this by 273. I got 506, which is in degrees Celsius. That's our answer. So let's now do number 24. So it's moving on a little bit more quickly because the questions are getting more generic, I would say. And that's great because we like problems that are not very hard sometimes. Let's do number 24 now. The Ksp of aluminum hydroxide is that. What is the value of delta G for the precipitation at 25 degrees Celsius? So hold your horses and don't just go and plug in this into our cool formula that says delta G naught equals negative RT ln K. Not yet. And that's because Ksp represents this reaction. Ksp is representing dissolving. So this would be the reaction that it would be describing, where aluminum hydroxide would be dissolving into, that and 3OH minus, and these are aqueous, and that's solid. And our reaction is completely flipped. So this reaction is defined by the Ksp. If we flip the reaction, so let me flip it, and I'm too lazy to write these things, so just assume they exist. And yeah, so we have this reaction over here, and notice how it's flipped. So if we flip a reaction, doesn't the K just become 1 over K? So this reaction has a K of 1 over Ksp. What's 1 over Ksp? 1 over 2.0 times 10 to the negative 31. That's going to be a gigantic number. 2 times 10 to the negative 31. You'll get 5.0 times 10 to the 30th power. That's a pretty high K, and because it has a high K, it's going to actually, favor products so much that it's essentially just going to move to the right. And that's why you have a single arrow over there, which makes perfect sense in my opinion. So Now we could use that famous formula. Delta G naught equals negative R. What's R? Well, we're in kilojoules because we want kilojoules. So 8.31 times 10 to the negative 3. T is 298 because we're at 225 degrees Celsius. And we're taking the natural log of this monstrosity. And let's see what we get. Yeah, I'm not a fast calculator typer, but I am fast enough to produce this answer in, less than 20 seconds. So this is what I got. And it should have 2 sig figs, but whatever. The answer is A. So that went along pretty well in my opinion. So let's move on to 25. 25, ammonia reacts with oxygen, and it's that reaction. Okay. It says the rate of change of nitric oxide is found to be 1.1 molar per minute. So it's saying that this nitric oxide is, being produced because this reaction is producing this stuff. It's being produced at 1.1 molar per minute. So what's the rate of change for oxygen gas? Well, we have to follow this stoichiometrically. Sorry, that word is kind of hard to pronounce. So let's think about this. For every 4 moles or molar, whatever, because if we're at constant volume, it really doesn't matter. If 4 molar of NO is being produced, then how much oxygen is being consumed? Well, there's 5/4 times as many oxygens that's being consumed than nitric oxides. So for every 4 moles of NO that get produced, 5 moles or molar of O2 become consumed. So notice how it's just 5/4 times as many, or 1.25 times as many. So if the rate of production of nitric oxide is this, then the rate of consumption will be 5/4 times as much, because 5/4 times as much of oxygen is being consumed according to the reaction. So we just do 1.1 times 1.25, and we get, well, 1.375, and that's just 1.38. Now it's being consumed, so it's disappearing. So the rate of change is negative A. There you go. Not so bad after all, huh? Now number 26 involves just one formula. A first order reaction has that rate constant, and for an initial reactant concentration of that, how long does it take for a concentration to fall to 0.15 molar? Well, we have to use that formula that we memorized, hopefully. The natural log of our initial concentration over our final concentration. And remember, this is derived from the integrated rate laws. And you honestly don't you honestly don't need to do these integrated rate laws. But, if you know how to do them, that's great. If you don't, just memorize them. They're not too bad to memorize. It's equal to KT. So let's look at this, and we know that the natural log of our initial concentration of this falls to that. So easy enough. That's equal to K, 0.320 times T. And we can assume that T will give us minutes, since the K is in minutes to the negative 1. So we can safely assume that this T will be in minutes, and that's our answer. So just make sure the units match whenever you do this, because sometimes they like to trick you. And that's not very nice, but that's what they have to do. So I solve for T. T is equal to 6.55 minutes, and that's C. And there you go. So now let's take a look at 27. Iodine monochloride, that thing, reacts with hydrogen according to their equation. So it's reacting with hydrogen to produce stuff. What is the rate law? Now they give you different concentrations and different initial rates. Now we have to know that for first order reactions, the change in the amount of concentration is proportional to the change in the rate. So in this case, keeping all else constant, if we double this, and we see that this doubles, then it's going to be first order, because they both double. By doubling this, the rate
increases by the same factor, which is the definition of first order. So that means that this is going to be first order, so ICL is just first. Now let's take a look at H2. So keeping these two constant now, we notice how if we half this is halved as well. And if you decrease it by a factor and the rate decreases by the same factor, that's first order. So that's why H2 is also first order. And you get, this because it's all to the first power. So there you go. Not so bad after all. So let's look at number 28. Which graph is linear for a reaction that has second order in A? Now it's D, because if we basically what ends up happening is that we do the integrated rate law for the rate of consumption of A, and you basically form a line when you graph this. It's complicated. Check out videos about the integrated rate laws to, learn more stuff. But if you don't want to, and instead you just memorize that second order is, will form a line if you graph 1 over A versus time, then, if you memorize that, you're all set to go. And that's why number 28 is D. If you want to learn more, remember, check out the video. I'll probably post it under the video description just in case you're curious or you just want to know why. Because why is a very important question in chemistry. Number 29. The reaction of nitrogen dioxide with carbon monoxide is that, and it has been studied, and the following mechanism has been proposed. So you got a slow and fast reaction. Remember, we look at the rate determining reaction since that determines the rate. The fast reaction doesn't really determine the rate because it's going so fast that it doesn't really matter. The slow one's what determines how long it takes because this one's slowing everything down and basically the time it takes for things to happen is just the time it takes for this to happen since that takes the bulk of the time. So that's what rate limiting reactions are in a nutshell. Now, we basically have to find the rate law for this. Now, the rate law for an elementary reaction, you just look at the coefficients in order to find the order. So in this case, NO2 and NO2 are each first order. So rate is equal to K times NO2 times NO2. Wait a second, you can combine these because they're the same thing. Yep, and that's all it is. So it's C. So let's do number 30. A reaction has a rate constant, K equals that, okay? And it has an activation energy of this, and that K corresponds to 45 degrees Celsius. What is a K at 25? Now, if you don't know the formula, you're like, what? How do you do this problem? Well, actually, there's something pretty cool. There's this cool formula. I don't know why I keep on mispronouncing words, probably because I'm talking super fast. So, in this case, we see this formula. Hey, we gotta edit this. So, notice how there's an EA, activation energy, there are Ks, and there are temperatures. Looks like the perfect formula to us. We don't even have to understand how it works. We just have to know that it works. We gotta just use it. So I actually have an alternative to this formula. So an alternative is you factor out the negative from this. So you factor out the negative. You basically get negative 1 over T2 minus 1 over T1 when you factor this out. And I like doing this because it puts a negative in front of there. And an alternative equation that you can get is ln K2 over K1 is equal to negative EA over R times 1 over T2 minus 1 over T1. Notice how just by adding a negative, it goes all in order. It's just K2, K1, T2, T1. The ordering is really nice, and, I like nice. And it also follows the ordering for this too. Because this thing is super similar to this. And notice how there's a negative in front. So memorizing this is far superior, in my opinion. So let's check out our layer 2, which is where the problems are. So got to go all the way here. Nope, that's too far. Let's go down here. So we're number 30. Let's use that formula that we just learned. Ln, alright, gotta change the layer. Ln K2 over K1 is equal to negative EA over R. Or you can just use the formula at the front. It's up to you. I like using my formula that I made for myself, even though technically I didn't make it, because it was discovered already before I was born, probably. So look at this. We can just plug in numbers now. So we know that, let's just make K2 the higher temperature and K1 the lower temperature for simplicity. So if you're lowering the temperature, then, our K2 will be the higher temperature, which is 45 degrees Celsius, and no one uses degrees Celsius. God always use Kelvin, and it's scientifically proven to work. And that will be at 318 degrees Celsius, and K2 in this case would be equal to 8.54 times 10 to the negative 4. And I don't know what I just said, but that should be a Kelvin. Sorry for that if you were a bit confused. Now we have K1, which is what I like to call the lower temperature. So K1 is at the lower temperature, 25 to 98 Kelvin. And this K, I don't know what it is, but we do have all the other values. So let's plug everything in. Ln of K2. We know K2 is 8.54 times 10 to the negative 4 over K1, who knows what that is. It's equal to the negative of our activation energy, 90.8, divided by R. What should we use for R? Well, we're dealing with energy, so R should be 8.31 times 10 to the negative 3. And 10 to the negative 3 is because we're dealing with kilojoules and not joules. If it was just joules, then you would use 8.31. We're dealing with kilojoules right here, so let's use kilojoules. So like that, and we gotta basically chug in the temperatures. T2 is a higher temperature, 318 minus 1 over 298. And from here on, it's algebra, pure algebra. So 90.8, negative 9.8 divided by 8.0 times 10 to the negative 3 times 1 over 318 minus 1 over 298. You gotta be a little good at your calculator to be able to solve these. So you gotta master your calculator. And this is equal to the natural log of this stuff over here. And we can kind of change bases. So I know that it's just e to the 2.306 is equal to whatever's in here. 8.54 times 10 to the negative 4 over k. Now this is just k. Oh, we forgot to say it's k1. K1 is 8.54 times 10 to the negative 4 over e to the 2.306. So you simply just do the math. And I got 8.51 times 10 to the negative 5 as our k. And I'm not going to care about units because the problem just gives me the units for free. So I'm going to take advantage of that. So 8.51 times 10 to the negative 5, pretty close to B by 0.03. So we choose B as our answer, and it is correct. And maybe they got 8.54 because of some rounding issues. And maybe they rounded early. Who knows, right? So let's move on to number 31 now. Let me erase all this first and get a fresh start. So we're halfway through the test, and it's been more than an hour, I think. So let's, continue and strive to finish the test. 31. For which reaction will Kp be larger than Kc at 25 degrees Celsius? So for this problem, you have to know a very special formula. This is a formula that you should know. Kp is equal to Kc times RT all to the delta moles of gas. And we went over this, but the moles, or the change in the moles of gas, is the moles of gas on the product side minus the moles of gas on the reactant side. So in this case, Kp will be larger than Kc. So this will be larger than this if this is greater than 1.
So when is this greater than 1? Well, if delta energy is equal to 0, anything to the 0 power is 1. But we need it to be greater than 1 so that Kp will be larger than Kc. So we need delta moles of gas to be greater than 1. Or no, sorry, greater than 0. Because if it's greater than 0, then that's a positive exponent, which will give us, a number that results from it, something that will be greater than 1. And in this case, if you're curious what RT is, RT is 8.31. No, actually, no. That's not 8.31. That's 0.0821 because we're not dealing with energy here. So we use the other R. So 0.0821 times 298. RT is actually 24.47. And you're taking it to the delta moles of gas. If delta moles of gas is 0, then this entire thing will equal to 1, and Kc will equal to Kp. But we need Kp to be larger than Kc. So we need basically this entire thing to be greater than 1. And to do that, all we need is for delta moles of gas to be greater than 0. Because this to any positive number will give us a number that's greater than 1. And if you don't believe me, let's try this. 24.47 to the 0.01 is actually 1.03. So basically, anything that's greater than 0 as the exponent will make the inside resulting number greater than 1. So which one of these answer choices will result in an answer where the moles of gas, or the change in the moles of gas, is greater than 0? So in this case, we go from 1 moles of gas to 2 moles of gas. That's a change of plus 1 moles because you gained 1 mole of gas. And you can also do 2 minus 1. So A is the answer, and B is wrong because the change in the moles of gas is negative 1 over here. Right here it's 0, and right here it's also 0. So A is the answer, because if you raise this RT to the second power, you will get a number that's greater than 1, and when you multiply that by Kc, you'll get a Kp that's greater than what you had originally. So a little bit of math theory there, but there you go. So let's do number 32 now. 32 is about equilibrium once again. So let's move a little to the right side actually. So number 32 states that we have a reaction at equilibrium when sulfur trioxide is added to a sealed bulb at a pressure of 2 atmospheres. It undergoes a reaction above. At equilibrium, 76% of the sulfur trioxide has reacted. What is the value of Kp at this temperature? So this looks like a problem that requires an ice table or an ice chart. So let's make that ice chart. So this is 2SO3, 2SO2, and O2, and they're all gases. So we start off with 2 atmospheres of this, and we have none of these two. And then when you react it, of course, it will necessarily go to the right side because there's nothing there. And yeah, so this is minus 2x plus 2x plus x. Yeah, that seems right. And you might be wondering, how do we find the x if we don't have the final concentrations? Well, it does tell us that 76% of the SO3 has reacted. So this negative 2x is equal to the change in the partial pressure of SO3. And it says the change in the partial pressure of SO3 was 76% of it. So what's 76% of 2? Well, that's actually just 1.52. So we can see that from this problem,
76% of the SO3, or in other words, 1.52 atmospheres worth of SO3 gas has reacted. So if it's reacted, it's lost. And that's why there's a negative sign there. So we can actually rewrite this and, make our lives just a bit easier and a little less complicated too. So we know that 1.52 atmospheres get lost, and for every 2 that gets lost, 2 gets gained. So this will be the same amount. But for this one, it's a little bit different. For every 2 that is lost, 1 is gained. So for every this much is lost, half as much is gained. So what's half of 1.52? 0.76. You essentially get 0.48, 1.52, 0.76. And all you do now is, well, you plug it into the equilibrium expression to get Kp. And notice how Kp is when everything is a gas. And we do have that. So, Kp is products of a reactant, the partial pressure of O2, the partial pressure of SO2 squared over the partial pressure of SO3 squared. Now, doing the math, you can just shove in all these numbers because they're all equilibrium or at equilibrium. So you can put them into the equilibrium expression to find Kp. So what's our O2? Well, it turns out to be 0.76. SO2 is 1.52. We gotta square that because that's right there. And 0.48 on the bottom squared. And doing the math, you can put this in a calculator to get this. I got, well, okay, I don't think I typed it right. Give me a second. 0.76 times 1.52 squared divided by 0.48 squared. That's going to be 7.62. And if you are going to follow sig figs, you're just going to have 2 sig figs, and that's 7.6b. So let's do number 33 now. Moving on to a topic that has to do with acids and bases. So hopefully you're geared up for that. The pH of pure water at 50 degrees Celsius is 6.63. Okay. pH of water is 6.63 at 50 degrees Celsius. What is the value of Kw at 50 degrees Celsius? Well, we know that at 25 degrees Celsius, we kind of know that the pH of water is 7, but it's saying that if you increase the temperature, the pH goes down. I wonder why. Maybe because the Kw changed? Well, we know for water is neutral, so that means the number of H plus is equal to the number of OH minus in water, right? And this is directly related to Kw. Kw is just H plus times OH minus because Kw is showing this reaction, essentially where you have water self-ionizing to produce the 2 ions that we know so well to be the acid and the base. So that's what the Kw is. And we can use this relationship to kind of figure out what's going on. So pure water is always neutral, no matter at what temperature. It's always neutral, which means that this thing always holds true. H plus equals OH minus. That's what neutral means. Acidic means that H plus is greater than OH minus, and you can guess what basic means. But for now, we're focusing on this one, and it says that the pH of pure water is 6.63. So what is the H plus concentration then? We know that pH is negative log of H plus, and it's saying that this water has a pH of 6.63 is equal to the negative log of H plus. Well, I don't know what that is, but what we can do is multiply both sides by -1, and then do this. 10 to the negative 6.63 is equal to H plus. And what do we get? Well, 10 to the negative 6.63 gives us about 2.34, and let's just keep track of sig figs.
is equal to H plus. And the reason why there's only 2 sig figs is because when you do inverse log, the number of decimal places becomes the number of sig figs. Cool, right? So that doesn't really matter because we don't really care about sig figs, as I said a million times before, since this is multiple choice. Wait, that's not right. 2.34 times 10 to the negative 7. Forgot that exponent there. Super crucial. Now let's find the Kw. So we know that H plus is equal to OH minus in pure water. So this concentration must also equal the OH minus concentration. And we know Kw is simply just H plus times OH minus. And if they're both the same, you're essentially just multiplying this with itself. So if you multiply twice, you're squaring it. And what do we get? Well, I don't know. I got Kw at 5.5 times 10 to the negative 14. And that turns out to be C, I think. Yeah, C is right. And look at that. We're good to go. So let's do the next problem. And let's try our best. So this next problem is talking about pH once again. Don't we love pH? Well, sometimes. So let's read the problem. Alanine, which is this gigantic thing, has Ka equals that and Kb equals that. Which species has the highest concentration at a pH of 7 in water? So if you didn't know, alanine is actually an amino acid. Now, does that mean it's acidic? Kind of. So let's draw this out because I kind of want to draw it out. So this is what alanine looks like. Let's figure out how to draw this. That's really weird. One second. I gotta undo all this because I can't see the subscripts. I kind of don't want to mess up. Alright, so let's redo this. N, there's 2 H's attached to that. That's attached to a C, which is attached to an H. And that is attached to a CH3. So, I mean, you could think of the C as connected to 3 H's, but I'll write it like this for simplicity. That's connected to CO2H. It looks like that. And what you might notice is that this side is pretty basic because that looks like NH3, ammonia, our favorite base. And this is a side chain that kind of looks like acetic acid, CH3COOH. So this side is acidic and that side's basic. Well, guess what? They kind of want to react because, you know, this one is essentially acidic and that's basic. So since they're right next to each other, they're essentially just going to react with each other. So that reacts with that, and you essentially just transfer that H over. So let's just draw out how this acid-base reaction works. So I'll put the lone pairs there, I guess. So this attacks the hydrogen, and we're referring to the Lewis acid/base theory. So it has to do with bases donating electrons and acids accepting electrons, just like that. And in the end, you kind of just get this. So you get 3 H's and that N will be positively formally charged, if that's even a thing. Kind of like that, and like that. And this one has too many electrons, so it's going to have a -1 formal charge. So this is essentially the substance that you get naturally, because essentially an acid-base reaction occurs regardless of, you know, what else is in the solution. In this case, we're just looking at a pH of 7 in water, so it's pretty neutral. But even though it's neutral, it can kind of, you know, react with itself, and when it reacts with itself, it doesn't produce any OH minus or H plus, if you notice. So that's kind of the reason why the pH is at 7, because it's not releasing any H plus or OH minus. Rather, it's just reacting with itself. So I just wanted to go over some quick theory to prove why this process where this weak acid and this weak base react is essentially super spontaneous. And I'll show you a little bit of proof. So let's say we have an acid HA and B, like that NH2 branch that sticks out. NHA would be that COOH with that H being that H. And this is a typical acid-base reaction. And we can see Hb plus and, NH3 plus on that branched chain. So kind of atypical, but basically you could think of these two as the sides of the molecule or the amino acid. And what you can actually prove is that the K is equal to the Ka, the K of this reaction is equal to Ka of the acid. So the Ka of, HA, and that would be divided by the Ka of the Hb plus. And Hb plus would be the conjugate acid's Ka. And I could show you the proof probably in a video about acids slash bases on my YouTube channel, but I don't want to prove it because I don't need to just yet. But you can kind of see how this works. So the Ka of that acidic chain is said to be that 4.5 times 10 to the negative 3. And that's divided by the Ka of the Hb plus. Where is our Hb plus? It's this thing. But how do we find the Ka of that? Well, we do know the Kb of this because that's the base and that's a Kb. Now, the Kb of this, if you do, okay, there's a rule that states that if you divide, I think, 10 to the negative 14 by the Kb, you will get the Ka of its conjugate acid. So that's the base. The conjugate acid is that one with one extra H. So we can kind of calculate that 10 to the negative 14 divided by the Kb to get the Ka of the conjugate. And all of this can be found in my YouTube videos if you're curious. So I got a Ka for that branch. Pretty small number, to be honest. 1.35 times 10 to the negative 10. And notice how you divide these two. I'll do it out for all of you. And that gives you like 3.3 times 10 to the 7. And that K is super big. So that means that this reaction will most definitely happen. And this substance will, self-ionize, I guess. Yeah, it does self-ionize. It auto-ionizes. Auto-ionize. And that's why the answer in this case is actually going to be D. Now, it's not B, because there's no way that this O minus can have an H attached to it unless the solution was acidic. So this substance exists in acidic conditions. Now, this substance exists when when all the H's are taken out. So in this original one, this was supposed to be basic and that was supposed to be acidic. Now if you had a really basic solution that had a lot of OH minuses, then that OH minus would react with that and would cause that to be O minus, which would give you C. So C only exists in basic conditions, and A, well, that doesn't exist at all because the substance likes to basically neutralize itself. So a lot of theory there, kind of complicated, but there you go. Basically, amino acids tend to like to be in its charged form. So let's now do number 35. Hopefully this one requires less theory and more math. What is the pH of the solution formed by mixing 25 milliliters of a 0.15 molar solution of NH3 with 25 milliliters of 0.12 molar HCl. So it seems like there's a lot of mass involved, and maybe that's your strong suit, maybe it's not, but regardless, we're going to try our best to solve this problem. So let's figure out what's going on. So we're mixing a weak base with a strong acid. So we can write a reaction for this. We know HCl, we could just essentially call it H plus, because once it goes in water, it's essentially just H plus. NH3 becomes NH4, just like that. So let's figure out what's going on. So we can assume that this reaction will go to completion since a neutralization reaction between a strong acid and a weak base will almost always be spontaneous. And it will be so spontaneous that you could just draw a single arrow, essentially. So in this case, H plus is going to be how many moles? Well, 25 milliliters is 0.025 liters times 0.12 molar. Let's see what that is. That's 0.0030 moles of H plus. So we can write 0.0030. Now what about our NH3? Well, NH3 is 0.025 times 0.15, and that gives us 0.00375. And let's find the final volume of our solution. So 25 plus 25, our solution will be 0.050 liters. That's super important because we're kind of diluting things by mixing two solutions. Now this is the important part. We got to figure out how much H plus is left. Well, guess what? None of it is left because it's the limiting reactant. And what you get left is 0.00075 moles of NH3. And I'm not following sig figs at this point. I mean, I should follow sig figs, but let's just not, because if I did follow sig figs, I'll have to stop there. So, I mean, we could do that, I guess. So this would be zeroed out, and 0.003 would react with 0.003 of this stuff, leaving behind just 0.00075. And how much of this is produced? Well, if this much got consumed, then the same amount got produced because it's a 1-to-1 ratio. And now that we have, all the moles of the stuff, we have this many moles of NH3 and we have this many moles of NH4 plus. I don't know if I put that plus there, but there's a plus there because that's ammonium. So let's look at our information. We also got the Kb for NH3. So how do you write the Kb? Well, you're going to put the base at the bottom, just like you would do for Ka, where you put the acid at the bottom, and this would be the conjugate base. And look at that. So you kind of just figure out what Kb is. The problem tells you that. Yay. We don't know what OH minus is. That's what we're solving for. What's NH4 plus? Well, we know NH4 plus is 0.003, so we're just going to plug that in. Just kidding. We're not going to do that. That's moles. We need molar to plug it in because we need to plug in concentrations. So what's our new volume? 0.05. So just divide this by 0.05. I got 0.06 molar. So let's plug that in. And on the bottom, it's going to be the concentration of NH3. Now, I don't know why I put brackets. It should be parentheses because we put the number in there, not the substance. So this is the NH3, and we just divide by the volume to get the concentration. So it looks like I got 0.000. Wait, no. I was looking at the wrong thing. 0.015. And look at that. We can solve for OH now. You take this, multiply by this, divide by this to get OH. So I do that. and I got an OH concentration of 4.5 times 10 to the negative 6 molar. And we could find the POH from this, and that's just taking the negative log of that to get 5.3, let's see, 5.35. And we know that 14 minus POH is going to be our, pH at 25 degrees Celsius, of course. So doing that, we got a pH of 8.65, and that turns out to be C. Okay, that's 36. C. There you go. Not too bad. We figured it out, and let's continue. So we're kind of getting close to the section where math starts disappearing, but we're not quite there yet. So let's look at this one. What is the OH minus concentration in a suspension of the antacid MgOH2? Let's visualize this. We have a suspension of MgOH2. What is a suspension? Well, it's basically something that didn't get dissolved, and it's just floating around. And if it's floating around, doesn't that mean that the solution is saturated and it couldn't dissolve that suspension? Well, yeah, we can conclude that the solution is saturated. And if it's saturated in the world of equilibrium, that means that it's at equilibrium. So guess what? We can use Ksp to do this. So the Ksp for magnesium hydroxide is Mg2 plus OH minus squared. And basically, since we know it's completely saturated, then it's at equilibrium. So we can assume that our concentrations are at equilibrium. So because of that, we can use K for this. Cool, right? So what's our K? 2.06 times 10 to the negative 13. We're going to figure out how to, what our variables should be. So a quick ICE table will help us do this. MgOH2, Mg2 plus 2OH minus. So we don't know how much there is, but basically there's a lot, and there's nothing here. And we're subtracting by x molar, adding x molar plus 2x molar. Look at that, we got our variables right there. And we ignore this because that's not part of the equilibrium. So Mg is x, OH minus is 2x squared. And we can do this. 2x squared is 4x squared. Sounds weird, but it's right. So it's going to be 4x squared times x, 4x cubed. So 2.06 times 10 to the negative 13 divided by 4. Take it to the 1/3 power or cube root it, up to you. Same thing, 3.72 times 10 to the negative 5 as x. Now that's not what the question's asking for. It's asking for the OH minus concentration at equilibrium. So what's our OH minus concentration? It's 2x. If x is this, well, the OH minus concentration is 2x, which is just twice this. So I multiply that by 2. Okay, that's not a 5. I don't know why we're at 5. It's 3. So multiply that by 2, you get 7.44 times... Whoa. What am I writing? 1 second. My brain just malfunctioned, and it's fixed. So that's the OH minus concentration, and it looks like the answer is A. Bravo. So let's take a look at number 37 now. 37 wants us to balance the equation with whole numbers and wants us to find the coefficient for carbon dioxide. So this is not a typical reaction. It's actually a redox reaction. So that means that we got to split it into a reaction that is oxidation and one that is reduction. Now it doesn't matter which one's which because we'll figure that out as we do the problem. And a huge hint for this one is that we're in an acidic medium because there's H pluses involved, and we have this acid guess what it's called? It's called oxalic acid because that's the oxalate anion. And yeah, so we are allowed to add H pluses and H2Os as shown in the reaction. So we're in an acidic medium. So in this case, we got to balance it. Now, what a good thing to do in this case is to find chemicals that are similar on the left and right hand side, and those typically correspond in each reaction. So let's start off with this one. Cr2O7 2 minus becomes Cr3 plus. So now we could add the H2Os and H pluses to hopefully make this work out. But first things first, there's 2 Crs, 1 Cr, gotta make that 2. And then 7 Os, that's 7 H2Os. And consequently, since we have 14 H's, we gotta add 14 H's on the left-hand side too. And these are H pluses, since we're only allowed to add these two. Now, this has a total charge of plus 12. Here is plus 6. So where are the electrons? Well, they're on this side. So on this side, there are actually plus 6 electrons. And when you add 6 electrons, it cancels out with the 12 to get 6, which matches the other side, which means that we're doing something right. And in this case, since we are adding electrons on the reactant side, it's actually the reduction portion, because reduction, remember, is when electrons are accepted. So now let's do the other half. So let me erase this stuff down here without erasing anything else, hopefully. And on this side, we're going to look at the rest of them. So this one becomes this. H2C2O4 becomes CO2. We got to add that 2 there. And guess what? We can add 2 H pluses there. And voila, we're done. But we're not done, because we got to add the electrons. This side has plus 2. This side has 0. So that means this side will have, well, actually, that doesn't seem right. Give me a second. I got to figure this out. Yes, we're going to add 2 electrons here, because what ends up happening is that we got to cancel out that plus 2 with a minus 2 to get the same charge on the left-hand side as well. So hopefully it didn't confuse you like it confused me, but we have this, and now we just have to add the 2 reactions together to get the net reaction, combining both oxidation and reduction. And you gotta cancel out the electrons, because that's how oxidation reduction reactions work. Because in the end, you shouldn't even see any electrons being exchanged within the reaction, because it happens within, and the net reaction shouldn't have any electrons, or else it would be considered either a reduction or an oxidation reaction. And because the overall reaction has no electrons, that means that it can't be either. So we shouldn't have any electrons left over. So to do the cancellation, we know that there are 6 electrons on the left-hand side and 2 on the right. So why don't we just multiply this by 3? 2 times 3 is 6. 2 times 3 is 6. 2 times 3 is 6. 1 times 3 is 3. Now adding these two together, we get this. So let me try to write this in a fluid way. And we notice how 6 electrons do cancel in the end. Becomes 2Cr3 plus 7H2O plus 6CO2 plus 6H plus. Notice how we can cancel out the H pluses to leave 8 H pluses here. Now, does this make sense? Do we actually have the conservation of mass? Well, yeah. 6 H's, 8 H's, 14 H's on the left, 14 H's on the right. What about the O's? We got 12 O's here plus 7 O's. That's 19 O's. Do we have 19 O's on this side? There's 12 O's here and 7 O's here. That's 19. What about the C's? Well, there's there's 6 C's and 6 C. What about the chromiums? Well, there's 2 chromiums. Looks like everything's balanced. What about the charges? Well, this side has a +6 charge. This side also has a +6 charge. Look at that. This reaction is balanced, and there are no outstanding electrons to worry about. And what's the coefficient on CO2? It's 6. So 37 is actually B. All right, let's do number 38 now. Number 38 states that according to the standard reduction potentials above, a substance that can oxidize only one of these metals, so they're talking about these metals, must have an E0 value of what? Well, we have to kind of figure this out by first talking about what the question's asking. So it wants the oxidation of one of these metals, but this reaction is the, reduction. So we gotta change it so that they're all oxidation reactions instead. So now I flip them over, so all of these reactions are now oxidation reactions where things are losing electrons, and the standard potentials are flipped to be negative because I flipped the reactions. So when we talk about oxidizing metals, what's going to oxidize those metals? Well, an oxidizing agent will, and an oxidizing agent has to oxidize other metals by making them lose electrons. So where do those electrons go? Well, the oxidizing agent will gain those electrons, so oxidizing agents actually reduce themselves. So, for example, we could take a metal M plus, and you need an electron added to make the metal M. And we are going to generalize this as our reduction reaction because we're finding a substance that can oxidize one of these metals. So it's got to be an oxidizing agent. That's an oxidizing agent because oxidizing agents reduce themselves to oxidize other things. And we only can oxidize one of these metals. So for a metal to be oxidized, the voltage here plus the voltage here has to be greater than 0. Because if you want stuff to be oxidized, it's got to happen. And things happen when the E net or E not net or whatever is greater than 0. So things happen only when the E is greater than 0. And we know that when we add the E of the oxidation reaction component and the E of the reduction reaction component, we get the E net. And if it's greater than 0, it's spontaneous. So we know that if we make this E over here basically greater than 0.34, like 0.35, then adding these two up will get us a positive E value, which will make it spontaneous, which will allow this thing to oxidize copper, for example. Now, we're not exactly looking at copper. Well, actually, we are, because we only want to oxidize one of these metals. Notice how if I make the E too big, it will be able to oxidize every single one of these, and that's not what we want. We kind of only want to oxidize this one. So we have to have at least 0.34, we know that, but can it be more than 0.8? No, because if this is more than 0.8, it'll be able to oxidize silver. We don't want that. We only want it to oxidize copper. So therefore, the voltage or the standard potential of, whatever metal or whatever substance we use, it doesn't even have to be a metal, has to be between 0.34 and 0.8. And that's why B is our answer. Now let's look at number 39. 39 is talking primarily about another electrochemical reaction. So let's take a look. All right, so what is the delta G naught value for the electrochemical cell below? So in this case, they're referring to a galvanic cell. And the reason why I think it is a galvanic cell is because all these delta G values are negative, which means that all the reactions that are happening are going to make it so that the final reaction will be spontaneous. And spontaneous reactions happen in galvanic cells. So we have to kind of think about this and figure out which one's the anode and which one's the cathode. And of course, we are going to have a metal wire, maybe with the voltmeter, to measure the voltage if we wanted to. So it looks like copper is being oxidized, so the anode would be copper. And once it's oxidized, these electrons will kind of travel. They'll travel. And then, of course, we have like a salt bridge between the two, which will allow ions to form in these solutions, because that's what the salt bridge does. And it will be explained in one of the future videos that I make, which I have not made yet. But this metal over here must be platinum, because that's the metal used to initiate this reduction reaction from nitrate to nitrous oxide, or nitrogen monoxide. So we don't have to get into too much detail here, but can you figure out which one's positively charged and which one's negatively charged? Well, if it's spontaneous, electrons like moving to the positive end. So since electrons are moving here, this should be the positive end, and that's the negative end, where it's being repelled away from. So it's a good way to think about that. But back to the question. Copper is being oxidized to copper 2 plus and an electron. Now, what about this side? Well, this side, NO3 minus, is going to be reduced to NO. Now, it gets kind of complicated here because we have to kind of think about what exactly is going to happen. Now, to tell you the truth, you don't actually need to figure out what the missing stuff is over here, even though you could. But to tell you the truth, this problem is asking for the delta G. And, well, wait a second. Isn't this reaction here and this reaction here? Well, guess what? I don't need to figure out anything. These reactions tell me all I need, so I don't know why I was doing this. I should read the question more carefully, maybe. So, we know that it's going to follow this order where copper is going to go copper 2 plus. So we will have to flip that. So let's flip that. Copper becomes copper 2 plus 2 electrons. That has a voltage of 0.340 volts. And of course, since we flipped it, it's going to be negative. Now, what about this other one? Well, we know that the NO3 minus is going to be reduced. So this is in the right form. So we're happy about that, right? Let's do that. And we do that, NO plus 2H2O. And that has, well, 0.96 volts. And we want to make it so that the electrons are the same, so that when we add up the reaction, we have like an actual reaction where the electrons are balanced, right? So remember, the delta G for this cell is the delta G of the reaction, and this reaction better be balanced. So we can multiply this by 3, 3, 3, 6. The voltage stays the same. Remember that, super important. 2, 8, 6, 2, 4. The voltage stays the same, and we have 6 electrons, as it turns out. So we add up the voltages to get the voltage of the net reaction, 0.34, and it's a negative 0.34 plus 0.96. I got a voltage of, well, no, that's not how you write it. 0.62 volts is the voltage of this electrochemical reaction. And guess what? There's a cool formula that we could use. Delta G naught is equal to negative NF E naught. Now N is the moles of electrons involved. We have 6 moles of electrons involved. Alright, so what we do is we plug in the numbers. So delta G naught is equal to negative 6 times F. What is F? Well, there are many ways to do this. You can check out the table, because the table gives you the value of F, surprisingly. So check out this table. This table has so much information. Okay, it can't be edited. But look at this. It tells us that I really want to edit it. All right here. 96500 joules per volt per mole. Let's use that. All right. So we're all the way here. No. We're down here. So I gotta readjust the layer. And here I am. So let's just write the units to be more visual, 96500 joules per mole times volts. What is the E of the reaction? It is 0.62 volts. And notice how nice the units cancel out to give us just joules, but we want kilojoules. So we'll fix that later, but negative 6 times 96500 times 0.62 will give us a delta G naught of negative 358,980 joules. And this is per mole of a reaction. And I just added that, but it's kind of optional. So we can change that to kilojoules by dividing by 1,000. And I don't know, let's do sig figs, why not, right? 359 kilojoules. And it's a negative, of course. So that's our delta G naught. And what answer choice is that? Let's find out. Negative 359. Hey, look at that. It is B. All right, great. Let's do number 40 now. 40 is an electrolysis problem. And electrolysis involves reactions that are non-spontaneous. But that's not really relevant to the problem. Let's just solve it. An aqueous solution of copper sulfate is electrolyzed for 1.5 hours with a current of 2.5 amps. What mass of copper metal is formed? All right. Well, in the solution, we have copper 2 plus. How many electrons does each mole of copper need? Each mole of copper 2 plus need? Oh, well, it needs 2 moles of electrons to be completely reduced and, to form a mole of copper solid. Remember, we electrolyze a solution in order to get out the ions and turn them into metals. And yeah, that's basically all you could do, because what else is copper 2 plus going to do, right? So in this case, we need 2 electrons for every 1 copper 2 plus. That's super important, as we will see. So it says that we run with a current of 2.5 amps. Well, 2.5 amps is 2.5 coulombs per second. Now, how many seconds are we running this for? Well, 1.5 hours is, 1 hour is 60 minutes, and 1 minute is 60 seconds. Boom, 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 boom. We're left with seconds. So 1.5 times 60 times 60, we're running this for 5,400 seconds. All right, what is this? We have a total of 13,500 coulombs being injected into the system. And this amount of coulombs will kind of precipitate a certain amount of copper out. That's super important. So let me erase all of this once again. All right. So now we have this 13,500 coulombs. Let's go back to that amazing table that I showed you, just in case you don't know your constants, because honestly, this table is super duper helpful. Hey, check it out. For every, dang it, I really wanted to edit that. For every mole of electrons, there are 96,500 coulombs. We could use that to our own benefit and figure out this problem. So let me go back to here. See how that table is super helpful? You can either memorize it or you could use it. And honestly, memorizing it is slightly easier because you don't have to check the table, and it saves you a lot of time. So 96500 coulombs per mole of electrons. Now let's check out this reaction over here. 2 moles of electrons for every mole of copper produced. Now, we're not done yet. I kind of want to finish this off because I want to convert moles of copper into grams of copper. What's a molar mass of copper? Well, I have it right here. And, well, actually, I don't have it. Let's check out the periodic table once again. So, going over here, copper is 63.55. Great. 63.55 it is. I believe those words. 63.55 grams. Now, see how the units cancel out? Cool, right? That's how all things should be. And you're left with grams of copper. So 13,500 divided by 9,6,500 divided by 2 times 63.55. I got, whoa, that's not what I meant to do. I actually rolled my pen over the surface. I got 4.45 grams of copper. And is that an answer choice? Well, I hope so. Pretty close to B. And B is our answer. Bravo, everybody. We just figure out that problem. Now let's do number 40. Under which conditions is the Nernst equation used to calculate cell potential voltages in a voltaic cell? So you might be wondering, what is the Nernst equation? Well, luckily for us, we have some resources to help us figure out what that is. It's actually this equation right here. And what this equation says is that the potential is equal to the standard potential, that not over there means standard, minus RT over NF, ln Q. It kind of looks like that delta G equation we used at non-standard conditions. So guess what? This equation is used for non-standard conditions. And that's actually the answer, as you will see very soon. Because there's no point in doing or in using this reaction at standard conditions, because if we did this at standard conditions, wouldn't that mean that all our concentrations are 1 molar / 1 atmosphere? Well, yeah. And if they are all that, then that means Q is 1. And if Q is 1, isn't the natural log of 1 0? And doesn't this just zero out and tell us that if we have standard concentrations, E naught is equal to E? That's kind of redundant because E naught is a literal definition of the E at standard conditions. So you wouldn't use this equation at standard conditions because you would just get E equals E naught. Kind of redundant. So that's actually the answer. And it's pretty cool if you think of it that way. So we only use this for non-standard conditions because at standard conditions, well, E naught is a literal answer and you don't have to do anything more than that. So we use the Nernst equation for non-standard concentrations only. Now, let's look at the other things that they give. Non-spontaneous reactions. Oh yeah, Nernst deals with spontaneous and non-spontaneous. That's wrong. Reactions at equilibrium? No. It gives E's that are not zero and not at equilibrium. Reactions of ions with the same charge? No. We could have used the Nernst equation for this, and look, the charges are all over the place. The D is wrong. Now, let's take a look at number 42. According to the standard reduction potentials above, cathodic protection of iron can be achieved by, wow, that's super complicated, but let's break it down. Cathodic, I think it's cathodic, right? Cathodic protection of iron. So where's iron? That's iron. And iron is a metal, so we're assuming that we're protecting iron from becoming iron 2+. We're protecting this iron over here. So how do we protect that? Well, we got to write out the reaction for, what would happen if it was not protected? Well, it would just become this. So, it kind of looks like that. And if the iron was not protected, it would oxidize, and that's not good. We want to protect it. So, what are we protecting it from? We're protecting it from something that can easily cause this to happen. So this is
an oxidation reaction. So it would be an oxidizing agent, and that oxidizing agent would reduce itself to oxidize the iron. So something like copper 2 plus maybe. I mean, hey, check it out. Well, let's figure out. This is 0.440 volts because we flipped it. And notice how if we add this reaction to the copper 2 plus becomes copper with 0.34. It's going to add up to like 0.78, and that's pretty spontaneous because E is much greater than 0. So obviously, something like copper 2 plus can easily destroy this iron and turn it into iron 2 plus via oxidation. We don't want that. So we want to protect this iron from things like copper 2 plus. Now, what can we protect it with? Well, we gotta kind of think about what we're doing. So cathodic protection actually involves us using something called a sacrificial anode. And why do we call it an anode? Well, it's going to oxidize in the place of iron so that iron doesn't oxidize. So what metals can we use that will oxidize in place of, iron? Well, I think we could use zinc in place of iron because look at this. If we think about this reaction flipped over, zinc oxidizing has a positive 0.763 voltage, which means that it really wants to oxidize. And if it wants to oxidize more than the iron, because remember, iron is 0.44, this is 0.763, we flip the reaction to make it oxidation. 0.763 means that it really, really wants to oxidize even more than the iron. And what about magnesium? Like, holy cow, 2.73. Like, remember, we had to flip it first because we got to show that it's being oxidized. This is the reduction. We got to oxidize it in place of the iron. We're using it as a sacrificial anode. And if it's 2.37, it really, really, really wants to be oxidized. So iron might be like, I want to oxidize. But magnesium's like, I really want to oxidize. And this sacrificial attitude, this altruistic behavior of magnesium, I don't know why I'm including biology, but this magnesium will really, really want to oxidize itself in place. So it will be able to protect iron from being oxidized because it will sacrifice itself for the greater cause. So in this case, magnesium and zinc are our favorite choices. There you go. 443, which is an acceptable set of quantum numbers? So let me make my pen a little smaller. All right. Which one's acceptable? Well, n is 1 can p. Well, no. I'm confusing some things. But basically, this is the energy level. So, like, let's say 4s, right? The first number is, the first quantum number of this would be 4. S would be 0. It's kind of a memorization thing. And then these two numbers involve, whether it's going up or down. So you would get positive 1/2 or negative 1/2 for the last number. For the second to last number, it's based on the position of the electron when you order it from the first line to the third line. And this would be for the p subshell. So, let's get that side. I'm pretty sure that you're familiar with this. If not, you can check out my videos, of course. All right, so let's check this out. Does 43 make sense? Okay, I don't know what I'm saying, but let's go back to these answer choices. All right, A, n is 1, so 1, and then if this is 1, then it would be 1p. Now, this doesn't exist actually, because this always has to be how do I put this? Let me think about this for a second. This number cannot be equal to this number. And that's because this number has to be less than or equal to this number minus 1. So what's 1 minus 1? 0. So the second number can be, 0 or less. So since that's 1 and not 0, then it doesn't work. So it's kind of like a weird rule. I don't know if I explained it correctly. But 1p doesn't exist. You should notice that because if you do the electron configurations, you know it's 1s2, and then 2s2, and then 2p6. Where's the 1p6? It doesn't exist. So that's another way to figure this out, and A's out. What about this one? 2, 1, 0, 0. Ooh, the spin can't be 0. It has to be plus or minus 1/2. What about C? 2, 1. So this would be 2p. And we know the p sublevel has, well, 3 slots because there are 6 electrons, 2 in each slot. So maybe this -1 means that it's probably here. So let's just draw all of them, honestly. And that -1/2 means pointing down, and it's in the -1 slot. So yeah, this makes sense. What about this one, D? 3. Ooh, what's 2? If 0 is S, 1 is P, 2 is D. Now, does this make sense? -3. I thought when you draw the number line, it only goes to -2. So how can it be -3, right? There you go. C is our answer. Yay. Let's do number 44 now. 44 is a little bit tricky because you don't know what a radio node is. So what a radio node is, in a nutshell, it's kind of confusing. But basically, there's a graph, and you have the electron density probability, and basically the graph goes up and down, and the points where it intersects, those points are where the electron density is 0, and this is going to be the radius. So let me try to reconstruct my thoughts. Alright, so these places are where the electron density is 0. And that means that electrons can't exist there. And of course, I said those are, which means the distance from the nucleus. So maybe at a certain radius, no electrons can exist there. But in other places, electrons can exist there. So that's basically what radio nodes are in a nutshell. Now, to figure them out, there's actually a special formula, N minus L, which is the second quantum number, by the way, minus 1. So which one would have the most radio nodes? Well, it's going to be one with the highest N, so they're all 4. Yeah. Now, you gotta subtract the lowest number to make the highest number of radio nodes. So what's the lowest L that, any one of them can get? Well, L can actually be 0, and that corresponds to the S sublevel, so A is our answer. Now, it's kind of complicated, but, I really want to draw this out, but it's low-key complicated. But basically, we could use this formula, and we could say that 4 minus 0 minus 1 is 3, so we all have 3 radio nodes. And what the electron density distribution would look like for this is that at the beginning, of course, I don't know, it would kind of like, this is so weird, like, at the beginning, of course, when you're at the center, where the radius is 0, where you're basically at the nucleus, there's going to be no electrons there. But as you get further, the electron density spikes up, and it kind of goes like this. So it intersected the graph, the x-axis once, twice, and maybe 3 times, and maybe it'll do that or something. Notice how there are 3 of them, and that's what radio nodes are. Yeah, alright, 45. This one's a bit tricky. Ionization energies vary from left to right across the periodic table. Factors that contribute to this variation include which of the following? So this one is super duper tricky. And the reason why is, well, it's tricky. So what exactly is ionization energy? Well, ionization energy is the amount of energy it takes to remove an electron. Now, what factors contribute to this? Well, changes in the effective nuclear charge. Yeah. So we're looking from left to right across the periodic table, so I don't know. You could think of sodium starting off, and then we're going all the way to, now let's not start with sodium, let's start with lithium, because I'm more familiar with those elements. We end with O, and then F, and yeah, so this is lithium. And notice how as you go to the right, we are basically having the same amount of core electrons. We're just changing the amount of valence electrons as we go from left to right. So this one would have 1 valence electron. This one would have 6 valence electrons. And these are very bad drawings. And F would have 7 valence electrons. And note that the middle one, 3, 4, 5, 6, 7, the middle one's a nucleus. So yeah, let me shade that in. Okay, I just completely ruined the color coding. Let's pretend that one is like a white circle. All right, so what is nuclear charge? Well, what nuclear charge is, well, first of all, let's establish that there are 2 core electrons because they involve the first 2 electrons that were added to H and He. So there are 2 core electrons, and remember, lithium is the 3rd element in our periodic table, so the 3rd electron will be over there. And the middle will have a +3 charge. So, if you think about it, the inside core electrons are -2, but the nucleus is +3. So overall, there's a leftover of +1 that's causing, the electrons to be attracted. Now, that's not really the legit reason. What's actually happening is that we have a nucleus, cool nucleus right here, and let's just say it has a +1 charge. Now, let's say we have a valence electron here, and let's say we have an electron here. Now, what ends up happening is that the reason why the effective nuclear charge for this picture is 0 is because what ends up happening is basically, this electron's attracted, so it's going to move toward there, but this electron's like, no, stay away. So they cancel out, and as a result, this electron is not really attracted to the proton at all. I mean, it is, very slightly though, and I mean, this is a really rough definition, but the cancellation of the forces kind of tells us what the effective nuclear charge is. And in this case, since there's 1 extra proton kind of not being blocked, then that extra proton will kind of like force this electron to be more attracted. And that's why a higher effective nuclear charge, and remember, effective nuclear charge is Zeph. Higher effective nuclear charge means the electrons will be more attracted to the nucleus. So this one has a Zeph of 1, this one has a Zeph of 6, this one has a Zeph of 7. And a good way to remember this for the main elements is that the number of valence electrons is the Zeph. Cool, right? Alright, so we established that 1 is true. That will affect the ionization energy, right? Higher Zeph for the same, they're basically the same electrons. They're in the same shell. So, if there's a higher effective nuclear charge, these electrons will feel more attracted than these. So these will have a higher ionization energy since it's harder to kind of pluck them off as they are more attracted because of the high Zeph. Now, what is 2 and 3? Well, 2 states that does the differences in shielding by valence electrons change anything? Well, before I get to that, let's do number 3 first to make this a little bit more clear. Differences in shielding by core electrons. Now, don't we agree that in a row from left to right, all of these atoms have the same core electrons? So, yeah, even though there might be differences in shielding by core electrons, so, let's draw a picture. That's the nucleus, right, with a very positive charge. Some core electrons are closer than others, and some are more effective at blocking in a way, like quote unquote blocking the positive charge than other electrons are. Some of them are better at blocking than others, and that does cause a difference in like how effective these core electrons are at kind of canceling out that positive charge and like lowering that effective nuclear charge. But the problem is that all of these have the same core electrons, and if they all have the same core electrons, doesn't that mean that it doesn't really matter if you go from left to right because the core electrons are all identical in a sense, and even though there are differences, like some electrons are better than others, they all share the same. So differences in like core electrons in kind of shielding the valence electrons from the nucleus, that difference doesn't really matter because that difference is shared between all of these. So that difference doesn't mean anything because all of them have the same difference. So this one's wrong. Now, what about differences in shielding by valence electrons? Well, oxygen, for example, has more valence electrons than lithium. Lithium gets no shielding from valence electrons because it's only one valence electron. It has no other valence electron friends to shield. But for this one, the oxygen, these other electrons can actually, sometimes these valence electrons move around randomly, and they can actually shield maybe this valence electron from the proton. So yeah, as you go from left to right, there are differences in shielding by valence electrons, and they actually matter because it's different for each one. Like this one has valence electrons to actually shield the other valence electrons, as opposed to this lonely one valence electron in lithium. So if you think about it, the differences in shielding valence electrons differs, and it really makes a difference in the Zeph. So, if there are more valence electrons, yeah, there will be a higher Zeph because we said it was 6, but maybe that Zeph will be lower because maybe some of these valence electrons will maybe take a shot and block this positive charge. And, this 6 is just theoretical. Like, there are other factors that play into how that 6 is formed. This 6 assumes that, in a way, every electron on the inside blocks the protons in the nucleus. But, we don't really factor in those valence electrons blocking other valence electrons, too. So, because these valence electrons can, cause the effect of this nucleus on, attracting the valence electrons, it can cause that attraction to change because, electrons can block other electrons. Having more valence electrons as you go from left to right, that can have an impact on how attracted these electrons are to the nucleus due to the shielding effects of the valence electrons. So it looks like 2 is actually right, and the answer is C. So, really hard problem, and if you got this wrong, don't worry, it's honestly a hard problem, as I just said. But if you got it right, great work. And let's move on to number 46. Which gaseous ion has exactly 3 unpaired electrons? So, there are 4 of them, and I don't have a periodic table in front of me. So, let me write all these down, and let me transcribe these onto the periodic table we have at the beginning. So, let's go all the way back to the very beginning, and that's the periodic table, by the way. So, periodic table, here we come. Where's our periodic table? I don't see it. Right there. All right. So let's zoom out and talk about this. So let me just, for a second, change the position of the paper a little bit, and let's take a look. So we need exactly 3 unpaired electrons. So let's take Fe3+. Now, we know iron is right there, and let's just do the abbreviated electron configuration, starting with argon. Argon. And then let's just do the shells. So we know this is going to be the 4th row, so it's going to be 4s, and these are all 3d electrons. So it goes 1, 2, so 1, 2, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and it's 3+, so we're losing 3 electrons. They get stripped off from the highest energy level first, and you're left with 5 unpaired electrons. Looks like iron is out of the ballpark. What about nickel 2+? Well, same idea here. We're looking at the valence electrons, by the way. So nickel has the first 2, and then it has an extra 8.
So 1, 2, 3, 4, 5, 6, 7, 8. Remove 2, we have 2 unpaired electrons. Oof. Let's try the other 2. Titanium, 4 plus. Where's titanium? Oh, it's the 22nd one. So 3D, 4S, titanium. 1, 2, and of course just 2. Plus 4, everything is gone. There are no unpaired electrons. Looks like D is our answer. Let's prove it. This is vanadium. Vanadium is 23. This is going to be 4S, 3D. Let's fill out the first 2. 1, 2. And then the other 3 electrons are right here. 1, 2, 3. 1, 2, 3. Now, if you're confused about what I'm doing, check out videos about electron configuration to figure out what I'm doing. But if you get what I'm doing, that's great. And look at that, plus 2, bye-bye. Ooh, 3 unpaired electrons. That's what we wanted. And we have reached an answer of D through 2 ways, actually. The first way is just process of elimination, and the second way is, well, just, figuring it out by just doing the electron configuration for this ion. So 46 is D. Let's look at 47. Which element has the highest second ionization energy? So let's look at sodium. Sodium, we know, is going to be, let's see, sodium is our 11th element, 11 electrons, 1s, 2s, 2p. And, that doesn't look right. Is sodium, wait, does sodium have 11 electrons? Yeah, it does actually. Yeah, 3s. I was just teasing myself. And that's 11. The first ionization energy is when we take this out. Pretty easy. But we have a stable, well, okay, the first 2 electrons are stable because that one energy level is completely filled. For 2, the 2s and the 2p are completely filled. Remember, that's the octet rule, right? And these are super duper stable. Taking an electron out is like pulling an electron away from a noble gas. And we know noble gases don't like their electrons being pulled away. That's why noble gases are so inert, because they're so noble to their electrons, they don't want to lose them. So that second ionization energy for sodium is going to be super duper high, right? What about magnesium? Well, magnesium is basically sodium, but with, wait, let me think about this. Magnesium, I wonder what element is that? Well, check out the periodic table to figure that out. Hopefully it's nearby. Magnesium, oh, okay, it's next to sodium. I was doubting myself there for a second. All right, magnesium. Basically just sodium, but with an extra electron and an extra proton. So we have 12, and we lose 2. Notice how it's super easy to just take that out, because there are only 2 valence electrons, and it's easy to just pluck them out because they're not part of this stable octet. So that's not the answer. It's going to have one of the lowest of them all. Now, sulfur and fluorine are a bit interesting. Fluorine actually doesn't have a complete octet. It has 7 valence electrons. And removing 2 to make it 5, yeah, that takes a ton of energy, but not as much energy as taking it out of sodium, if you think about it. Because sodium is part of an octet. And you also have to think of it this way. All of these involve, well, okay, let me think about this. Fluorine involves taking electrons out of the 2s and 2p sublevels, but that's where its electrons live. Where fluorine has, I think, 7 electrons, so 1, 2, 3, 4, 5, 6, 7. Just kidding, it has 9 electrons. Now, in this case, we're taking an electron out of the 8th electron in the 2s2p. Pretty hard, right? Because the 2s2p electrons are pretty close to the nucleus, and they're pretty attracted to it. Same case here. Everything's close, but you're not taking it out of an octet, so it's kind of easier. So F is out of the picture. And sulfur, well, sulfur is, I don't even know, it's under oxygen. And all I know about that is that you're taking electrons out of the 3s and 3p sublevels. And let me just do this for sulfur. So it's, it has 6 valence electrons. It's kind of easy to just take out 2, because not only is it farther, you're also getting closer to the fact that you don't have a complete shell. And if you don't have a complete shell, it's pretty easy to take out electrons. And the main reason why I'm saying that it's hard to take out electrons from an octet is primarily because of something called the effective nuclear charge, the ZEF. Yeah, right? Let's think of a noble gas. A noble gas has no valence electrons. And that's probably because, actually, no. What am I even saying? 4, 5, 6, 7. Noble gas has 8 valence electrons, and that means it has a ZEF of 8. And that's why it's super hard to take out the electrons. But guess what? For something like 3s3p, yeah, the ZEF might be 6, but, the effect of the ZEF is greatly reduced when you consider how far away these are. So the second ionization energy will be super low. Well, not super low, but it'll be lower than what it would be for sodium or even fluorine, as a matter of fact. So C is out of the picture. And, well, I want to think of it one more way. The second ionization energy is taking out the second electron. So if you take out second electron, that second electron lies in a place where the ZEF is, let me think about this. We have 11 protons, right? Because this is sodium. And we basically have only 2 electrons to as the core electrons, because these are now the valence electrons once you take this out of the picture. That's a ZEF of 9. 9 is gigantic. So taking it out is super hard. So you could look at it in terms of ZEF, I guess, because, the higher the ZEF, the harder it is to take it out, and the higher the ionization energy. So that one is just a bit of, thinking, and eventually you'll get the answer. So let's take a look at 48. The ions below are listed in the order of increasing radii, except, take a look at this for a second. We're number 20. No. We're all the way down here. That's not right. All right, we're kind of down here. No, we're not. Where did I put the questions? That's awkward. Here we are. All right, so number 47 was established to be A, and number 48 is going to be interesting, but it's not that bad. So increasing radii, meaning that if they go in order, it better get bigger and bigger. Now, if you notice, if you look at a periodic table, you'll notice that aluminum has the most. You'll notice that all of these are isoelectronic. And what does isoelectronic mean? Well, isoelectronic means that they all have the same electron configuration. So isoelectronic. And what ends up happening is that if they have the same number of electrons, and the electrons are kind of arranged in the same way, the element with the most protons will be the one that will be the smallest. So this one has the most protons because aluminum has, I think, 13, magnesium's 12, sodium's 11. So the more protons, the higher the ZEF. Wow, right? The ZEF is still, heavily involved in determining these things, because, wait, let me think about this. That doesn't seem right. No, it's not the ZEF. Just kidding. It's more so because there are more protons, so more protons means more attraction. So that's why aluminum will be the smallest, because it'll pull all the electrons in, making the radius super small. Now, what about this one? Well, it turns out that for number 48, this one actually works too. And that's primarily because, I really wish I had a periodic table in front of me right now. but we don't. So what I'm going to do is I'm actually going to transfer these to my periodic table that I have on this to make this a little bit easier for me to visualize. It's hard to do these questions without using a periodic table. All right, let's take a look at the periodic table now, because I think it's a lot easier to do it. All right, so we take a look at this periodic table. Let me zoom out for a second. All right, there you go. So looking at this periodic table, I'll write out the second combination because honestly, I don't really know where the placements of the elements are, and I want to be really sure about it. K plus, Cl minus, Sc2 minus. So that's K, K, and then Cl, and then Se. So we're circling that one, and that one. All right, so we're going from smallest to biggest. We can see that these two are isoelectronic because they'll have the configuration of argon. And K has more protons, so it'll be the smallest, second smallest. But this one will be the largest because, guess what? It has the configuration of krypton, which is bigger. So this one's good. Now what about this other one that I found? Let's see. I wrote this one. Cl minus, Br minus, I minus. Now you're going down the period, so it'll get bigger, so it's good. What about O2 minus, F minus, Na plus? Well, O actually has 8 protons, 9 protons, 11 protons. This one should be the smallest, not the biggest, because they're all isoelectronic. So the only thing that matters is the protons, and this is in the wrong order. So we kind of just figured out the answer. Good for us, right? So let's actually go down here and say that the answer is D. Huh, I don't know why I can't circle it. No. Oh, it's because I'm on the wrong layer, of course. All right, number 49. How many sigma bonds are present in P4? So how do you draw P4? Well, it's actually interesting. There's actually no really other way to draw it, except for this way. You'll see what I mean. Each P needs 3 bonds, because phosphorus has 5 valence electrons. Let's bond it like that. So that one has 3. This one has 3. 1, 2, 3. And you connect it, you get this little shape, and we call that a tetrahedron. And it might be hard to visualize, but essentially you kind of have, let me actually look at this for a second. I'm getting confused now. So it's basically like this, kind of like that. And think of that as the base, and think of it as see-through, and this is the back, and then these two are the front. Kind of hard to visualize, yeah, but if not, great. So notice how each of these P's have, 3 bonds. That means 3 valence electrons added, and all of these are happy, even though the bond angles are super duper small, which is definitely not what they want, because the bond angle there, if you think about it, should be around 109.5. And that's primarily because the steric number, or the number of things, 1, 2, 3, 4, is 4. So that angle is not 109.5, but this is the reason why that's super unstable. How many sigma bonds are there? 1, 2, 3, 4, 5, 6. 6 of them. So 49 is D. 50. Phosphor theory, the molecular structure of IF5. So I's in the middle, and it's going to form an expanded octet. It's going to go F, 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 and F. And remember, 7 valence electrons. So these are the 5, and that's the last 2. And of course, these fluorines each have their own. We could draw those if we wanted to, but not really necessary since we only want the shape. The shape of this, yeah, think about this. This lone pair will repel everything, and you kind of get this shape. What is that shape? A square pyramid. Square pyramidal is our answer.
Number 51, formal charge on CO. So when there's 6 electrons, like, if there are 6 electrons in a bond, that's a triple bond. Oop, that's an O. And you have a lone pair there and a lone pair there. The formal charge on oxygen, that's the number of electrons it has to have minus the number of bonds minus the number of electrons that are not bonded plus 1. 51 is A. So we're on a roll here. The questions are getting a bit easier, but don't worry, they'll get hard soon. And not in the way you might expect, unless you've already seen how these tests are like. So these are the last questions. What's the valid Lewis structure for NO3-? Well, let's check it out. This one violates the octet and is in period 2. You can only do an expanded octet in period 3 and above. For this one, I don't know, like -3 and a +2 formal charge? That's unstable. What about this one? Ooh, breaks the octet, and that's the answer. Now this one's the answer because this nitrogen has a positive formal charge. You got 2 negatives. Now that's okay because it's not like +2. That's like insane. This one's like more tamed. That's why B is our answer. Number 53. Based on MO theory, what species has the highest bond order? Now, MO theory is super complicated. But basically for these things, what I want you to do is to draw kind of like this, where this is 2s, okay? Well, in this case, it is 2s because we're dealing with oxygens. So this is going to be, let's see, I'm trying to think about this. So, okay, I got it. So this is a sigma bond, and this is a sigma bond. It's an anti-bonding, so we call that anti-bonding. And honestly, you don't even need to know what it means when you solve this problem. Not relevant, but if you want to know about the theory, check out the videos that I made. If not, just watch what I'm going to do. So you're going to create some kind of tower, and that's going to be 2p. Notice how 2s, there's 1, yeah, like, regular 2s, and s always has 1. They'll always have like this anti-bonding. It's like, it's doppelganger, essentially. But the doppelganger will kind of cancel out the effects, as you will see when we do bond order. So this is your sigma and your 2 pi, and you're going to have pi anti-bonding pi orbitals and the anti-bonding sigma orbitals. Super weird, but basically you're going to put an oxygen on each side, and depending on, what the charge on our oxygen is, that matters a lot. So oxygen with a negative charge, that thing is called, let's see, I'm trying to think. It's a superoxide. So fun vocabulary. O22- is peroxide. This one, I don't know. Not important. So basically what MO3 states is that the number of bonding electrons minus the number of anti-bonding electrons over 2 is the bond order. So we kind of know that oxygen has how many valence electrons? Well, each one has 8. 2 oxygens has 16 valence electrons. And what about this one? This one, O2 plus, well, 16 valence electrons. Wait, what am I even saying? It's not 16. O2 has, each oxygen has 6, so 6 times 2 is 12. Yikes. Okay, this one has 11, because it's plus 1. This one has 13. This one has 14. So the minimum number is 11. 1, 2, 3, 4. You fill this tower up. 7, 8, 9, 10, 11. Now, we want the bond order to be as large as possible. So to make it as large as possible, we got to make sure we're not subtracting a lot of this anti-bonding electrons. So notice how if we go from 11 to 12, we're going to add another electron there. Well, no. It's actually going to be over here. But when you add that, it makes this bigger and makes BO smaller. So at 11, we're happy. Adding any more will kind of make the bond order smaller because we're adding more anti-bonding electrons. So that's definitely not what we want to do. So A is our answer. And if we kind of plug it in, we can find the bond order for O2 plus. And, let's just say bond order of that. Number of bonding electrons, 2, 4, 6, 8, minus the number of anti-bonding electrons, 2, 3. All over 2, 2.5. And, yeah, that's the answer. And if you're wondering, oxygen has a bond order of 2, which kind of matches the number of bonds in oxygen. It's a double bond, right? So they're kind of related. All right, we're almost done here. 54. Let's zoom in for this one. When I zoom in, it causes the entire screen to go to another place, this unknown land that I don't know. All right, where is the place I seek? It is over here. All right, let's check this out. How many carbon atoms can be described as sp2 hybridized in this model? All right, remember, sp2 means a steric number of 2. That has a steric number of, no, wait, sorry, a steric number of 3. I don't know what's going on. Remember, 1, 2, 3, because S is 1 and 2p is, 2. And that adds up to 3. So that has a steric number of 3 because there's 3 things. That does not have a steric number of 3 because it's attached to 3 hydrogens and 1 bond. That's a steric number of 4. No. What about this carbon? Well, I'm confusing myself now. I think I drew too many lines, and it caused me to think that, okay, that line is not drawn by me, because I thought I drew that, and I was confused. But that's sp2. That one's also sp2. What about this one? Yeah, it's also sp2, because there are 3 things, which is a steric number of 3, which is sp2. So the answer for this one is D. Not bad. Number 55. Which compound contains 4 collinear carbon atoms? Now, if you know from a little organic chemistry, hopefully you know how to draw the branches. If not, I'm going to quickly show you. So for this structure over here, let's just draw the line structure for this. So when you draw lines, what's going to happen is that each endpoint is going to be a carbon. So that carbon is that carbon is that one. And there's a double bond there connecting it to another carbon, and then a single bond connecting it to another carbon. And then you're going to have the O and the OH. Notice how all the carbons are not shown. They're shown as like endpoints of each line, and the hydrogens are not shown because you can infer from this that there's 1 bond, then the rest are hydrogens, and there can only be 3 more bonds, so there's 3 hydrogens there. It's a quick overview of how to draw these things. But yeah, notice how I draw them as bent. Why do I draw them as bent? Well, because that's going to be 109.5. That's going to be 120 degrees. Notice how it's 120 degrees, not a straight line. So you got to find collinear. Now, let's draw all of these using the line structure that we learned. Butane. Now, if you don't know your organic nomenclature or organic chemicals nomenclature, I would research it a little bit, but butane, but 4, ane, all single bonds, 1, 2, 3, 4. 4 carbons, 4 endpoints. That's completely bent. That's not right. Cis-2-butene. Butene, 2 double bond. So it's a double bond, and it's at the second carbon. So but is 4 carbons. So cis just means that it points in the same direction. So it kind of looks like that. So the double bond's on the second carbon, right there. So we call that second carbon. And no, that's bent. So let's continue. Trans-2-butene. That. Nope. 2-butyne. Well, this is the answer because we said everything else was not. So 2-butyne. Butyne is a triple bond. So 1, 2, 3, 4. Now you might be wondering, why didn't I bend this? Why didn't I do this? Well, it's because these are sp hybridized. Sp means, sp essentially means that you only have 2 things connecting to something, and that's linear.
180 degrees. 180 degrees. 180 degrees. So D is our answer. Okay. 56. Which substance exists in a boat and chair configuration? There's no way of you knowing this without taking basic organic chem or just coming up with the idea. But basically, in organic chem, the very first thing, well, not the very first, but one of the first things you learn is that there's chair, and that chair can become a boat. And this configuration is more stable than this one because there are electrons that are repelling each other, not good. But if you put those electrons, electrons are part of the atoms, right? If you put them separated, this is the best configuration. It's a chair. And this, if you notice, is using the line structure that we just learned. Let's count the carbons. 1, 2, 3, 4, 5. Oh, wait. 1, 2, 3, 4, 5, 6. 6 carbons, all single bonds in a cyclohexane. Cyclohexane adopts boat and chair configurations. Yay, free knowledge. 57. Which of the numbered carbons in nicotine is chiral or stereogenic? Now, for something to be chiral, in a nutshell, you got to be connected to 4 things. You don't count electrons, by the way. It has to be actually 4 atoms. And the second part, they all got to be different. A, B, C, D. Let's check out which ones satisfy that. The first one, connected to 3 things? No. Second one, ooh, there's only 3 things, and there's a hydrogen there. Remember, it's connected to hydrogen because the hydrogens are not written out in the line structures? Potentially. Let's check out 3. Nope, it's connected to 3 identical atoms, even though there are 4. This one, nope, there are 2 hydrogens there. That doesn't work. So the answer is 2. B. Not so bad, right? All the following are monosaccharides except, well, you actually have to use prior knowledge to know this, and the answer is sucrose. Sucrose is a disaccharide. I don't really know how to spell that, but it's a combination of glucose and fructose forming a friendship together, or they're basically linking together to form the polymer, which, there's 2 of them, so it's a disaccharide, and, it's called sucrose. Fun facts, right? Ribose is in RNA. That's a monosaccharide. Fructose and glucose are all monosaccharides as well. Last 2. What is the product when 2 molecules of ethanol undergo an aldo condensation? Let's be honest, I don't know what that is. And if you do, good for you. If you don't, it's okay. Because let me tell you a trick to get this question 50% of the time right. So let me teach you how to do that. 2 molecules undergo some kind of reaction. So I'm going to assume that they combine because they look pretty big, okay? If I combine these 2, how many carbons are there? There's 2 C2H4O. Let me just combine this structure. 2 carbons, 4 hydrogens, and 1 oxygen. Double it up because we're going to combine 2 of them. Your final product better have 4 carbons, 8 hydrogens, and 2 oxygens. This one has 4 carbons, 3, 5, 7, 8, and 2 oxygens. I like this one. What about B? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6 hydrogens. Oh, no. This one, nah. It's too unstable. Look at that. Like, who would want to form that? Like, that's basically a square. Well, it's actually not a square, but basically, you are creating bond angles that are definitely not ideal, and that creates some problems, and that's not good. And why would something want to form this shape, especially since it's like a square shape, the angles are going to be close to 90, and we know that they like to be 135. So, it doesn't really make much sense. Wait, no, not 135, sorry, 109.5. Alright, so what about D? 1, 2, 3, 4, there is 8 hydrogens and 2 oxygens. It's A or D. So choose the one you like. And if you chose the letter D, you got it right. If you chose A, it's okay. Maybe next time. Number 60. Which molecule will have the longest wavelength absorbance maximum?
That's confusing. Even I don't know what it's talking about, but we can think about this as, you know, um, the longest wavelength. So if you think about this, wavelength and frequency are inversely related. Higher wavelength equals lower frequency. We want to find the one that's the lowest frequency, or the one where the bond basically doesn't I don't know, like vibrate the most often. So it's going to vibrate the least often. All right. The stronger the bond is, the lower the frequency is because it's stronger. It's not going to vibrate as much when being disturbed. So, I mean, I don't even know if this is the legit way of doing it, but it will help you get the answer right. And that's the point of this. Hopefully someday I'd learn what this is. But for now, well, actually, I know what this is, but I don't understand it very well. And especially not when I'm comparing stuff, because usually you're just given the values for the absorbances, not um, you don't have to compare them between. So that's a weird question, and weird questions require weird solutions. So obviously, C and D are out because we need to think with double bonds. Double bonds are what will create the longest wavelength. Now, what's the difference between A and B? Well, the only difference is that that double bond is moved, to this side. Well, actually, is there more of a difference? Let's see. There are four. Okay, they're both the same thing. Honestly, at this point, you guessed 50-50. If you liked choosing the one that was more symmetrical, A, you got it right. So good job. So that's all for this test. Super long. I think this thing lasts for 3 hours. I'm so sorry, but I don't really expect you to watch all of this. Just watch the parts that you need help on. And hopefully you learned a lot, and have a nice day, everybody.